All right, so as people are trickling in, I guess I'll just start introductions. So first, if you haven't done so, please re-download the repository. Pretty much what got added along with a bunch of data sets is all of the lesson material that I plan to go over today. I had opted to end up doing that just in case we start running out of time. I don't have to just start typing everything. I can just slowly start scrolling through the page depending on how we are with pacing because there's a lot of things to cover, I realized. Um, and so a little bit about myself. I am a graduate student at Virginia Tech. I just finished my courses, so I'm a PhD student. I'm not yet a candidate either. Um, I am also a instructor for software carpentry, so a lot of our data sets actually come from them. And I think that's it. So if you've downloaded the repository or either through Git or as a zip file, and you open up the Jupyter notebook, um, so hopefully there's someone to help you if you have issues with that. All of our data is in this data folder. The notes I'm going to be working from are in this 01 notes folder. And just for me as this lesson, so I don't start overwriting my notes, I'm going to create a second folder just to dump everything in that I'll be presenting. You guys can do that if you want to follow along. And then just as a backup, if we really start falling behind, I'll just go through the contents of this notes folder directly instead of live coding everything. So, all right. All right, so, yeah. Oh, the address, yeah. Yeah, so on this page, there'll be a little green button that says clone or download. If you click it, if you know your way around Git, there's a Git URL that comes with it. If you don't, there's a download zip button that you can click, and that will just download everything as a regular zip file that you will unzip. All right, cool. Am I good to start? Just raise your hand if you still need this link up, and I'll just leave it up. All right. So I guess I'll keep doing intro stuff. So this is the introduction to Pandas tutorial. Essentially what Pandas is, if you come from NumPy, the easiest way to describe it is it's NumPy, but you're allowed to have heterogeneous data. If you come from the R world, it's pretty much the R data frame. And if you don't come from any of those, it is a programmable way that you can run your Excel spreadsheets. Is there anyone here? I know there's at least one people who program in R who have touched R in their lives. Cool. So I will be making a lot of R references, so that should help you kind of bridge the gap. I learned how to do all this stuff in R, and then a lot of the data manipulation tasks kind of just carried over to Python. So I think after looking at this for at least a year, they look kind of similar. So we'll see. Am I good? Does anyone still need this link up? Just raise your hand and I'll just think of something else to say. Okay. What else to say? So I am using the latest version of Pandas, which is 0.20.1 as of, I guess, last night. If you're running on something older than that, there's going to be certain things that don't work anymore, and I found that out yesterday when I was putting together the lesson plan. So I will mention that to you just because that's also in my notes, like this used to work and why doesn't it work? But there's a few things that no longer work or are getting deprecated before they make the 1.0 release. So, and I have no idea when that would be. They keep saying soon. Between Python 2 and 3, at least for this tutorial, there is only one case where there's an actual difference, and that's when I write a function that uses the division sign. So I'll mention that if you are on the Python 2 version. Otherwise, everything should just work. The last time I gave this tutorial, at PyData last year. I literally had to ask someone in the audience for like a Windows computer that had Anaconda, so the installation should be okay. Shouldn't have been too bad. There's very, very few dependencies if you just install the entire Anaconda distribution down. All right. Can I take this link down now? Anyone else need a link? Because I'm running out of things to say. All right. Oh, I can write it on a whiteboard. SciPy. All right. It's good to know I have a whiteboard. All right, so here's the Jupyter Notebook. So Pandas is a special library in Python. And so for those of you who are absolutely new to Python, Python comes with a lot of tools already in there. Some you have to download, some it just comes with if you just install regular Python. But a lot of these packages, you actually have to import them. So the package that we are importing is called Pandas. Oh, yeah. And for those who are new to the Jupyter Notebook, each one of these cells are code cells, so you can run regular Python code in them. You can also do some other stuff that I won't go over. And to run it, you can hit Shift-Enter, and it'll run that block of code and give you a new one. If you hit Control-Enter, if you hit Control-Enter, it'll just keep running that block of code, and it won't go to a next cell. So. If you need to check the version of Pandas that you are using, like I had to yesterday, it's pandas dot _ version _. And so I'm running 0.20.1 right now. All right, so in Python, or if you're trying to use a function that's part of a package, unlike R, you have to actually tell Python where exactly to find all of these functions. So Pandas has a nice function called read_CSV that lets you read CSV files. But if we wanted to actually use this function, we have to say pandas, which is the library or package that we're using, and the read CSV function. So the first data set that we're using, so the way my folder structure is set up right now is I'm in this folder called 02 lesson. I have a separate folder for my data, and then all my notes are in the 01 notes folder. So for me to get to my data, because I'm in a separate folder, I actually have to say 2 dots to say, hey, look one directory up, go to the data folder, and then our first data set is this gapminder.tsv file. Just by looking at the file extension, it's TSV, so it's tab separated. So the function is defaulting to a comma separated file. So the way we can read tab separated files is we add another parameter to the function. In this case, there's a delimiter parameter, and we say \t to say, hey, every new piece of data isn't delineated by a comma, it's delineated by a tab, and \t lets you do that. You can see here, all Pandas did was dump out our data set to the screen, right? So that's not particularly useful other than we just loaded and saw the contents of our data. So what we can do is save this to an actual variable. So I'm going to pick a variable called df and do the same function again. And now if I say df in the cell, I've actually saved everything to the right-hand side of the equal sign, got saved or assigned to the thing to the left side of the equal sign. A useful thing that you're going to be seeing very often is this method of a data frame called head. And instead of dumping out the entire contents or most of the contents of this data frame, all it does is gives you the first 5 rows. So it just makes it a little bit more manageable just to see what's going on. A lot of times you're going to see people write their import statement as import pandas as PD. And what this allows you to do is you get to say the same exact thing as before, but instead of typing the word pandas, you say PD. It's called an alias, and some of these packages end up being a little bit too long, or you're going to be using a lot of functions within it, and so this just saves you a little bit of typing. And just to show you guys, this does exactly the same thing. There's this generic function in Python called type, and what type does, if you ever get confused as to what's going on, or if there's an error that's saying it's expecting one thing, but you thought that's what you gave it, run the regular type function on your object, and you can see here it's saying that this df variable is a pandas data frame object. So after you load up your data set, what do? You probably will look at the head of your data set. That usually helps you see if your column names got loaded up properly or if your data just got loaded at all. Another thing that you might be that you might want to know is looking at the number of rows or columns of your data set. So you can use the attribute shape to get the number of rows. That's what shows up first. Let me make this bigger. And the second number is the number of columns. So this shape is an attribute. So if you had, for example, thought it was a function or a method, you would get an error. So that's sort of something that you'll learn over time, what things required are set around brackets, what things don't. So just something to keep in mind. I usually forget things like this all the time. And the next other thing that you'll be doing a lot after you load up a data set is running this method called info. And what info is going to give you, the first line is essentially the type of the object that you gave it, or type of the object. So this is a data frame. It's going to say that this data frame has 1,704 rows, and it's got 6 columns. And then each column is going to tell you how many, in this first part, it's going to tell you the column name. The second column is going to tell you how many non-missing values that you have. So this data set, we don't have any missing values. And then the last column is going to tell you the actual data type of that column, right? So in NumPy, everything is some kind of number, but in Pandas, each column can be a different data type. And that's sort of the benefit, or that's sort of what Pandas gives you. So the first thing that we're going to go over are just the absolute basics of how do you pull rows or columns out of your data frame. So I can say, if we just wanted the country column, we can say df, a set of square brackets, and then in quotes, the column that we want. So country. And that'll give us just the country data frame out. We can save this to a variable, and then now if we want to use country df again, we can use it like that. Another common syntax that you'll see floating around the internet is df. If you're just trying to pull one column out, you can use dot and then simply call the single column that you want directly. If it does, you have to do it in, so if a column has spaces, you have to specify it the first way, otherwise this won't work. So this is really just a convenient way for you if you just need one column. I've sort of seen around the internet that, it's really just for convenience. Don't rely on this behaving exactly the same as this every single time. And one example of that is deleting columns. So if you need multiple columns, it's the same set, it's the same syntax. You have your data frame, you have a set of square brackets, But in order for you to provide multiple values, you have to give it a list of columns that you want. And so a Python list is, you create a Python list using square brackets. So that's why if you need multiple columns, you'll see two sets of square brackets. So if I wanted the country column, the continent column, and the year column, and I can just say, just give me the first 5 rows, that's how I would subset the columns that way. Yeah. So if I hit, so I've been creating, because how I've been creating it is, if I hit Shift Enter, it'll run it and then create a new one underneath. If you want to manually create a new cell, you can say Insert Cell above or below. Yeah, Shift Return will run it and then create a new one underneath. So yeah. Oh yeah. So if you wanted to just get the column names or headers, there is an attribute called columns, and we'll play around with columns in a little bit. But if you just need a list of just all the columns, that's how you would run it. Yeah. So typically, I would run head on my data frame just to see the column names like this. But if you have like thousands, yeah, you'll probably end up just getting it out like that. Yeah, so there is. So it used to be you can write something like that and say, give me column 0. You can't use it this way anymore. I'll show you. There's other ways that you can get the index out. But, that used to work. So so if you need to delete a column, there is a general command in Python called del for delete. And if you wanted to delete the country column from our data frame, you would say del and then that. This would actually not work. So that's why people on Stack Overflow actually say you should probably get used to writing your code like this. This is really just for convenience. And there's actually like Python handles or reinterprets the syntax actually a little bit differently, which is why this bottom command won't work, but the top one does. The other way you can delete a column is using the drop method. And here you say you drop the column that you want. And then you have to say access equals 1 to say you're dropping the column. And we'll go over a little bit about what accesses are in down the line, but that's how you would drop that's another way you can drop a column. The only way with this is if you run this, it'll drop the column, but if you look at your data frame again, it doesn't get saved. So you actually have to save that value if you want to drop a column in this way. Or there's another parameter called in place that you can set to true, and then that'll just drop the column in place. That way you don't have to do this reassigning or having this data frame getting copied in memory. I believe you do, because yeah, so by default, the axis is set to drop rows. So you actually have to say, hey, I'm actually going to drop. This is how I'm specifying dropping columns. Because these row names can also have labels. So it's going to be looking for the continent row label, and that's probably not going to work. All right, so. All right, so we're going to reload that data set again because I just messed it up. CSV. Oops, PD, pandas. So that's pretty much how you would subset different columns. So if you have a very large data set, probably the first thing you're going to do is just pull out the column that you actually care and not just use everything. But another thing that that you'll end up doing is start slicing or looking at different rows of your data. Maybe you only care about a few, like a certain range, or you just want to spot check something, some kind of row, just to make sure your data set got loaded properly. So there are 3 ways you can subset rows. 2 of them are going to be moving on, and the last one is sort of deprecated. So the first method is using this LOC attribute, I guess. So LOC allows you to pull out different rows of your data, but it pulls it out by what the row was labeled. So in this example, when I say pull out row 0, it's going to be the same thing as index 0, just because our data frame is just labeled in order from 0 to 1,700 something. And this also shows you Python is 0 indexed, so if I wanted the first row, I'll pass it 0. If I wanted the 100th row, I would pass it 99. Those of you who've programmed in Python before will know that if you want to count backwards from a container of some sort, you can use negative numbers. But in this case, LOC won't work because it's going to be looking for the label, the row index, -1, and that doesn't exist in our data set. So if we really wanted to use -1, how would we do this? So there's another way you can slice rows, and that's using iloc for index location. I'm guessing that's what it means. So if we give it 0, that's going to give us the same exact thing as before, but this 0 is actually the first position in our data frame. So if we say iloc 99, that would also give us the same exact information. The difference here is -1 will now work because it's actually saying, hey, pull from index -1, not the row label -1. Yeah. Yeah. So you can label your rows however you want. You can have gaps. That's sort of I'm not going to go over like time series things, but yes, like sometimes you're going to have some kind of period of time and you need to just fill in the dates in the middle, so you can insert like random dates as well, and it'll just create rows for you. So yeah, you can relabel any part of this data frame. Yeah. Yeah. Yeah, so just to reiterate, if you start sorting these things, the label follows the row. So you then have to be very careful if you're using iloc, if you're always referring to the first element or the label that just got shifted after you sort. There's another way that's getting deprecated that I found out yesterday when I ran this, is IX. So I'm really just showing you guys this just for people who are using an older version, or you'll definitely see this on the internet. So this does exactly the same thing. If you're running a newer version of Python, it's going to say IX is deprecated. Please use LOC or ILOC. And there's a bit of documentation there. Essentially, what's going on with IX is it's going to behave like LOC first. So it's going to look for the row index label or the name. And if it can't find the name, then it's going to treat it as if you're giving it an index position. So the actual position in the row position. So IX0, IX99, or IX -1. Why doesn't that work? Okay. I don't know why that's not working. All right, I'm going to skip that. So in general, so far I've just shown you how to pull out one row at a time. If you want, you can give it another set of square brackets, just like we did with pulling out columns. And you can pull out columns that way as well. The way IX behaves, it's going to be looking for the label first, so we get the same label out. It just so happens in this data set, the label and the index are going to be the same. So we can also use this notation. So just to stay with IX for a little bit, this notation can also be used to subset rows and columns, and this is sort of when this looks very much like how you would subset data frames in R. You have this set of square brackets, you have a comma. Things to the left of the comma is how you define how you're going to subset the rows. Things to the right of the comma is how you're going to how you define how you're going to subset the columns. So if I wanted to say get the 0, 99, and 999 rows, and I can also say give me the country, life expectancy, and GDP per cap. Oops. That's how I would be able to subset both rows and columns. And you can do the same exact notation using LOC, because this is basing this off of the name. But had I done this using ILOC, this would not work because I have specified my columns using labels, not the actual position. So if I wanted, I could specify 0, 3, and 5 if I wanted to get the same information. All right. So using this type of notation, you can also do what's called Boolean subsetting. So let's say life expectancy mean is going to be df life expectancy and mean. So a lot of these columns, so each column ends up becoming what's known as a Pandas series. So just think of a series as a column. These series all have various built-in methods. The mean is one of them, so you can easily pull out a column and run a basic summary statistic on it. So in this example, I am calculating the mean on the life expectancy. So this is the, I guess, 59 years old. That is the life expectancy across all countries, across all years in our data set. Probably not a very useful number, but I guess that's that's actually pretty high given how far back this data set goes. But you can use this LOC method to subset your data just based off of based off of some other condition, right? So I can say, give me the, actually, let me back up a little bit. So LOC, remember, things to the left of the column is how you're going to subset rows. Things to the right is going to be how you subset columns. So if I wanted to say I wanted all the columns, I can put a colon there. So that's Python slicing syntax for just give me everything. So I'm going to say, hey, give me all the columns, but I want to filter out the rows. So I can say life expectancy greater than the mean value I calculated, and that'll give me back all of the rows in my data where life expectancy for that row was greater than the average life expectancy calculated across the entire data set. All right. Ooh, actually doing pretty good on time. All right, so just as the end of, I guess, part one, one really other cool thing that you can do with pandas is called grouped or aggregate statistics. And this is actually a concept that's really powerful and carries on to all of the other tutorials that are going on, like the Dask one, like down the hall. So what ends up so let's say we wanted to calculate the average life expectancy for each year in our data set, right? That's a question that we're going to have. That's a question we're going to have about this data set. We don't want the average life expectancy in our entire data set. We want a year-by-year breakdown. So what a group by statement will do is you can say, hey, I want to pass in this variable called year. Essentially, what you're going to do is subset your data set, your data frame, by each unique value in there. So each unique value of year, essentially, in your mind, you can think of gets its own separate data frame. And then you pull out the life expectancy value, calculate the mean that way, and then you can get a life expectancy count for each, an average count for each year. All right. So the way we do that is we can say there's this function called group by. In the R world, this is sort of like a t-apply if you're in base R, but if you're in like the tidyverse worth of things, it's actually called group by as well. So we're going to group by each year, and you can see all this does is gives you back a group by object. So nothing actually got calculated yet. It just tells Pandas that if you do make a calculation, make those calculations on each subset of year in this in our example. So here I'm going to say I'm going to pull out, break up my data set by each unique value of year. I can get the life expectancy column out of it, and then calculate the mean. And so this did roughly the same thing as before. So if you just ignored that part that I highlighted, what we did before was we calculated the life expectancy, the average life expectancy in our data set. And we say group by year, what it's going to do is parse or partition our data by each unique value of year and then calculate the mean there and then stitch it back together. So group by statements, another common term that you'll hear is called split, apply, and combine, where you split your data set into various parts. Each part is essentially independent from another. You apply some function, meaning in our case, the function that we're applying is the mean. So it's going to, for each partition, calculate the mean, and then combine it back together so you get one final data set at the end. Right? So this paradigm of splitting your data into isolated partitions to run a calculation, putting it back together, that's sort of the cornerstone of how distributed computing works. So this kind of method actually carries on, or is very scalable and carries on as you progress in your data analytics careers. Yeah. Okay. So first, this group by year, essentially under the hood, Pandas just knows if you make a calculation, I'm going to have to break it up by year first. Because this ends up being a so this is, you can think of it as a regular Pandas data frame. It just has some special marker attached to it saying that if you do anything, split me up by this variable first. So since I have essentially a regular Pandas data frame, I can pull columns just like I pulled columns before using regular square brackets. So this part of the syntax or code that I've highlighted, if you ignore this part, the group by part, that's really the same as, hey, I have this data frame, I'm pulling out the life expectancy column and calculating the mean there. The part that I inserted, this group by, all it says is everything to the right before you end up making that calculation, break it up by the variables that I specified. In this case, it's year. Yes, so this notation here is just like what I did right up here. So pulling out columns is square bracket and then in quotes the column that you want. Yeah, that's actually my next example. But before I go there, I actually do it this way first, but I go through both examples too. So you can actually pull out multiple columns, and remember, if you're pulling out multiple columns, you have a second set of square brackets. So in this case, let's say I'm doing life expectancy and GDP per cat. Now I've broken up my data set by each year, and I'm pulling out the life expectancy and GDP per cap, and then I'm calculating the average for each of those. And then, if you wanted to put multiple group by statements in here, you can. The syntax is just like before. If you ever need more than one of something, you surround it in a set of square brackets. So we can say, let's group by year and continent. And then this will say for each year and each continent, the average life expectancy or the average GDP per cap. So it's a very powerful way to quickly, if you have like a relatively clean data set, this is a really good way that you would be able to explore your data. So another thing that you'll see people do, because you already see this line of code running off the screen a little bit, is in Python, if you put a backtick behind something, it actually tells Python, hey, the next line that you'll see is actually the line is continuing off to the next line. So what you'll see people do is do something like this. Oops. I'll use fewer spaces or not. Is it not like that? I don't know why it's turning red. I think it just doesn't like two spaces. But you'll see people write their code like this as well. So you'll say, and it makes it a little bit easier to read as well. So you can say, I have my data frame. The first thing I'm going to do is a group by. Then I'm taking the mean of whatever I group by. So you can just read down the line and get a rough idea of what's going on. Another way you'll see people write that, instead of using this backtick, you'll see people just surround everything with round brackets. And that's another way Python knows that treat everything between a set of round brackets as one command. So you'll see people write their code like this as well. Yep. Yeah, it should be backtick return, and I'm gonna ask a helper to help you with that. All right. He's having a weird backtick syntax. Yeah. All right. So the next thing that you'll. Oh, okay. I think I. After the dot. All right. Yeah. Yes. Yeah. I'll do that like way later. Yeah. This is supposed to just get you interested and convince you that this is a useful tool. so, so one other thing that we can do, that's not what I'm looking at. All right. Yeah. So we can look at group by each variable continent, and then pull out the country, and then there's a method called nUnique that lets you count the number of unique values. So in here you can say for each continent, we're counting how many countries there are in each continent. So Oceania is, I guess, just Australia and New Zealand. But these are ways that, like, when you first load up a data set, you're checking. This is the process of checking to make sure that, one, is your data set complete. I'm pretty sure this doesn't have every single country in the world, but it looks complete enough from what little knowledge I know about this data set. But there aren't like blaring, like very obvious errors that are like coming out to me at the moment. So yeah. Um, I'll get there. Yeah, we'll get there. For now, we're just going to assume that we don't have any missing values, and then when I first show you a step that includes a missing value, we'll go over that. And so the last thing I want to go or just show you, or if you guys aren't convinced enough, so let's say this is the group by year and get the life expectancy. So all I've done was set a variable to the average life expectancy for each year. Pandas is pretty cool in that there are plotting methods built right in, and that's not working because matplotlib.pyplot, that's plt. I think I'm gonna have to say so this is all right. So this line of code, I'm pretty sure I have to import matplotlib to use the second line, but essentially what this code is doing is whatever plot gets rendered in the Jupyter Notebook, please display it underneath my cell in the Jupyter Notebook. If you don't, you're going to end up saying something like plt.show, and then it'll show up as a pop-up window. So again, so Pandas is pretty cool. There are plotting methods built straight in. So since we gave it a series of values here, it knows how to plot them without doing too many more bits of code. Yeah. How far? Oh, yeah. Oh, yeah. So one way that I do it, so I come from a statistics background, even though I'm not a statistician. I work with a lot of statistical data sets, so a lot of our data sets are actually flat. They don't have this hierarchy. So in this, and I'll go over this again later on as well, but um, if you look at the output of this, it looks a little bit different. There's like this weird indentation thing going on. Um, so one thing that I will do if I want a completely flat data set again is there is a method called reset index, and then that will just completely flatten this data set, and then I can use that in my processes. So that's usually what I do. It's just because in the data sets or type of data that I work with, I prefer it to look like this and not some weird hierarchy. Um, So usually when I'm done doing some kind of group or aggregate, I end up running reset index. So then this actually becomes a regular data frame like we've been working with this entire time. And you don't have to think about, oh, this is some weird hierarchy. The syntax is a little bit different. So that's how I avoid it. I'll leave that there. All right, cool. All right, so the next thing, or the last thing for part one, is how do you save these things out? So I have this vector of average life expectancies per year. You can see that this is actually a Pandas Series object, not a data frame anymore, and that's because of the way it was calculated. So the labels are now this year, and the values are now this the average life expectancy. So if you wanted this to be a regular data frame again, I run reset index, and then I get my regular data frame where I have a column for year and a column for life expectancy. And this is a regular data frame that I expect it to be. So I can save that to a variable, That variable looks great, so now I want to save this out. So each data frame has a function to underscore, and then it saves to something. So you can save it to a CSV file, you can save it to an Excel file. There was an HDF class yesterday, so you can do that. Bunch of different ways that you can save out things. If you care about, if the most universal file type is a comma separated value. So what you can do is what you pass in this to CSV is the location you want to save it to. So I'm currently working in this 02 lesson folder, so if I say 2 dots, it brings me to a folder above. And then I have a folder called output, and then I can say life expectancy by year.csv. Right? And so what that will do is save out our CSV file. So if I show you guys this, where is it? Oh, I just spelled it wrong. Oh, it's up here. Let's spell this correctly. And let's also delete everything in here. All right, so I have this life expectancy by year data set. If I look at it, you see that that kind of looks right. I have some empty column, but then I have my year column and my life expectancy column. And in this case, each row has 3 elements. So the row index label actually got saved with our data set, right? That's just the default behavior of 2CSV. But if you don't want that, which chances are you don't, you run the index equals false command, and then that will give you whatever, it'll get rid of the index. So if your index isn't anything special, like all it's doing is keeping count of the row number, you can pass in index equals false. It'll make your file sizes a little smaller, and it won't get loaded when you reload this data set. For the people that work between R, work back and forth between R and Python, you actually have to install this separately, but there is a file type called feather, and it is a binary type that will save out from Python, and then it gives you a feather data type that you can load straight into R. And it's a binary file, so it'll be smaller and load a lot faster than a plain CSV file. The rule of thumb is you can totally use this if you're just bouncing back between 2 languages. Just don't rely on Feather for long-term storage because it's not that stable yet. So I've been told. Right. Cool. And yeah, I actually don't know. This looks like you give it a database connection and it'll just dump it to a table. Is that what it does? That is what it does. Yeah. Yeah. The people at Continuum, I think it's Continuum. Well, it used to be part of the Blaze project, but there is a library called Odo. I think I can just Google this. Yeah, Odo for the Star Trek fans. Odo the Shapeshifter. So there is a library called Odo that essentially you give it a incoming data type and an outcoming data type, and it figures out all the ways to traverse a graph to make that happen. So your mileage will vary about how this works, but you can go from like, I don't know, CSV is like such an easy example, but you can go from like a SQLite to like a JSON file, and it'll figure out all the weird ways to convert them. The only issue with that is like some of those steps are you're gonna lose information in them, so there's nothing you can do about that. But if you just need something at the end, you can use Odo as a library to help you do that without writing or figuring out the intermediate steps yourself. Cool. All right. All right, that's part one. We're doing good on time. All right, next thing is data assembly. So you have a data set, and typically, or at least in the data sets I work with, sometimes they're large enough that they're in separate files, and so your next job will be to put them together so you have a single file. So since this isn't I don't know what's going on. This should be a new notebook. All right. So in the new notebook, so we have to re-import pandas. I have 3 data sets for you guys, and these are toy data sets. So there is concat1, concat2, and 3. So this is what it looks like. So they're all pretty much the same. They have the same columns, they have the same row labels, but they're just 3 data frames that we're going to concat together. Oh, sorry. So all of our data frames look like df1, just the insides are a little bit different, so you can tell them apart. And so what we're going to do, so this is an example of, let's say you want to concatenate your data row-wise. So that's actually pretty common. If you have 5 million rows, a data set that's 5 million rows, you might have it broken up into 5 sets of 1 million rows each, just because that might be the limit that you can send as an attachment in email or something. So however you get your data, data might come in pieces. Time series data, if you're just collecting like logs or something, and when you finally do your analysis, you're gonna have to concatenate your log files together so you have a single data set to work with. So the first thing that we're going, can I, just raise your hand if I can move on, like scroll down. All right. So the first thing we're going to do is concatenate our data row-wise. So we've been using the read_CSV function, but Pandas has another function called concat, and it lets you concatenate data sets. So concat takes a container of, or a list of data frames that you want to concatenate them together. So we have our 3 data frames, df1, df2, df3. And if we run that, you'll see that all it did was concatenate our data together. I'm trying very hard not to say stack because that's an actual Pandas function. But if that word helps you in your mind of what's going on, then say stack. Just realize that's an actual function in Pandas. And so all this did was take our data frame and just append it to the end of the previous one, and so on and so on. They don't have to match, and I'll show you that. And they don't even have to be in the same order. It'll know, and it'll realign them. Which index? Like this? So these just come with pandas, like that's just a row number by default. So if you never have them, can you get rid of them? I don't think you can get rid of them. Yeah, you can. Yeah, you can get rid of them when you save out, but they're always going to be there. Whether or not they're useful to you, that's up to you. That's up to you. Yeah, those are row labeled. So yeah, that's my next point. So you'll remember that LOC subsets by row label. So if I do LOC now, it's pulling out all the 0 labeled rows. So now I get 3, just because that's what happened when I concatenated our data. So if you really wanted the first row, you would have to say ILOC. So yes. Is it reset index? There we go. Yeah, yeah. So, I forgot how we. There is a way to do this. There's a way to do this without making this look funky, and I'll look it up during a break. But yeah, you can totally. So what I did was I kind of made it worse, but I fixed the problem. So that's sort of. So that's also up to you on how you want to handle that. there's a much cleaner way to do this. I know that for a fact. But yeah, I'll just get rid of that, even though it's recorded forever. All right. So another thing that you'll have, especially if you're creating data in, if you're building like a data collecting pipeline, you might end up creating a vector or a row of data that you're going to want to stack or append or concatenate to existing data. So we can create a series by saying pd.series, and we can say n1 for new 1, new 2, new 3, new 4. Right, so this is our series, and if we wanted to, or if we expected to be able to concatenate them together, F1, you'll see that it didn't exactly do that, but this behavior is actually what concatenating is doing. So our new row, if we look at it, if you end up turning this into like a data frame, it's going to end up with a column called 0 just because it never got a label, so it's going to just give it 0 or 1 or 2, et cetera, et cetera. And then all we're doing is concatenating by default will concatenate things, just bind it to the end of the row. So that's exactly what it did, was we had this new data frame that had a column called 0, and it just tacked it on, and because there wasn't a 0 or column named 0 already, it created a new one and just stacked or just tacked on our data at the end, right? So that's not exactly what we want. So if we wanted to actually create a row of data and then append it or concatenate it the way we expect it to, we can create a data frame. So the way you can create a data frame is capital D, capital F in the Pandas library. You give it the values that you want, so n1, n2, n3, n4. And then because concatenating will automatically align the row, the column names, or the columns, you have to specify columns. Columns. So we can say this is A, B, C. Actually, I'll flip these last two just to show you guys that it will automatically align this. What is this? Uh-oh, did I forget a bracket somewhere? What? N1 through 4, that has a bracket. Oh, I need double brackets, sorry. Yes, I even have in my notes. Note to double bracket. Okay, yeah, so we have a new data frame that's ABDC, and if we run pd.concat on this, on df1 and new row 2, you'll see that it will concatenate our data and then also realign, or it will know which columns, it'll realign based off of the column names. So you don't have to worry about, oh, is the data that I'm appending in the right order? It'll know that and do it accordingly. Yeah. Yes. Oh. Yeah, so when you end up with like a single row, it'll come back as a series. Um, so yeah, they are different objects. So that's a behavior that you kind of see in R as well, is like when you get a single vector of something, it comes back as just a vector, which is just the series object, not a data frame object. Yeah, so this is actually a data frame object. And essentially a series object is always like one row or one column. So if you ever have more than one, then it's probably a data frame object. Yeah. Cool. All right, so last example. What if you end up, this happens a lot if you're like web scraping or something, you're collecting data, and not every single web page in the site has the same amount of information. So you might have, you might collect data that's not exactly the same, or like have more or fewer rows than your actual data frame, your final data frame. And so this works as well. All that's going to happen is the columns that don't match will get a missing value. Right. Yeah. Yes. So if you end up like N4, N5, B, C, I don't know, something like this, that'll work too. It'll just fill in missing values. Oh, yeah. That's the next part, yeah. At least I know that like I'm pacing the lesson well if your next question is like exactly what I'm doing next. Yeah. You can, I don't think you can do it in this step like in one go. You would have to like replace nans with 999, which is very common in like health data sets. So when I go over missing values, I'll show you how to do that. All right, cool. Concatenating columns. So if you want to concatenate columns, so the R way is cbind, so our row bind is what we were just doing. It's exactly the same function. The syntax is pretty much exactly the same. The only difference is there's another parameter called axis, and we set that to 1 if we want things to operate row-wise. And again, you'll see that all it's doing is just mashing these things together. And so if you have repeated column names, it's going to do exactly that. No, yeah, it's not these. None of these are like unique identifiers. The index position is a unique identifier. So if you need something that's like absolute, like give me the first one, that's one way you would be able to get that. Oh. Do you know off the top of your head? I'll do it.
I guess my suggestion would be
Probably fix that. Yeah, probably fix that before you go on. Yeah. Or job security in your code, right? But that does segue into the next part, which is how do you rename like your columns? So I showed you before, if you say dot columns, that gives you the columns that you have in your data set. So if you can easily reassign that just by saying dot columns is equal to whatever you want your column names to be. So I will reassign all of them, actually. Actually, I kind of went through this example, so I guess we can maybe skip this one. So if you want, oh, actually, that didn't help at all. That's exactly the same thing. So I can call this D, E, and F. All right. So if I wanted, I can reassign my column names just like that. And if you try to concatenate them together, it'll align the columns just like before. If you want to rename the rows, for example, so the row index, the way you do that is instead of columns, it's dot index, and you can give it whatever you want, 0, 2, 5, 7. Right, so you can rename these as well. And that's when you will end up using the difference between LOC and ILOC if you want to start differentiating the first row or just the actual 0. And then just to finish off the examples, the rows will, oops, the rows will also realign themselves as well. So this is one of the cool things. If you do work with time series or time data, and your row index is the date or some date time object, and you start concatenating things together, it will align itself so you don't end up with like a mess of a data set. It gets very useful for time series things, but I'm not going to show you time series things. Yeah. Like sort them or yeah, so the way I've been doing it is I essentially do the column subsetting, but I specify it in the order that I want, and that's what I use as a column subsetter. So, all right. So the next thing that you will do, so this is if you just have a large data set that's just broken up into pieces. But another common task is merging data when you have different data sets that you want to merge together. So for the SQL people, these are like doing table joins. And you can do that as well in Pandas. So we have 4 data sets that we're going to load. So there is survey person, data survey site. So these data sets actually come from the software carpentry SQL tutorial or lesson. It's in a SQLite database, but I sort of just wrote it all out to a CSV file. Survey. All right. So we have these 4 data sets. There's this person data set about people on this Arctic exploration. There's a site of where they've taken readings. There's the survey where they actually performed a set of readings at a particular site. And then there's a visited data set that tells you who visited what site on what day. All right, so a very common task is if you're going to do some kind of analysis is put all these tables together into one giant data set. So the way we do that is we can say, actually, first step is I'm going to subset this visited data set first. 2, 0, 2, 6. All right. And this is just so I don't have duplicates, so I can show you the next example. So if any of you are familiar with joining tables, there's a few different ways you can join tables. They all end up using the same exact syntax. It's just what happens. So there's something called a one-to-one merge, where if you have a series of values and another series of values, and there's no duplicates in either of them, and you just want to combine those 2 data sets, that's essentially what's a one-to-one merge is. And you'll just get a one-to-one alignment of your data. Another type of merge that can happen is if you have one data set and another data set, but the second or the first one of them has duplicate values in them. So you'll end up doing a many to one or one to many type of join. And what ends up happening there is the data set that doesn't have duplicates will get duplicated in the one that does. And then another thing that can happen is if you have duplicates in both data sets that you're trying to join, and what ends up happening is what's known as a Cartesian product, where every pairwise thing gets created and you end up with way more rows than what you expected, but sometimes that's what you want. So the syntax for all of that is exactly the same. You just have to be mindful of what your data set contains. And then whether if you're doing one-to-one or many-to-one, et cetera, that really just depends on what's in your data set. So how do we actually do these merges? So there's this one-to-one merge. Pandas has a function call merge. So there's two ways that you can do this. So I'll show you the first way. If you're also in the Jupyter Notebook, if you hit Shift-Tab, it'll give you the function signature. So that's how I've been seeing this. Another, I guess, trick is if you say pd.merge and a question mark, it'll give you the actual help docs. So if you just need something to, jog your memory without Google, or if you don't have access to the internet, that's always there for you. All right, so when you're doing these merges, this is pretty much universal. The language is universal. There's this thing called a left data set and a right data set, and then, or on camera, it's left and right. So you specify a left data set, a right data set, how you want to join them. So this is an inner join, so it'll only keep the values that have matches. You can do a left join that will keep all the values on the left side and then merge values on the right. So you'll end up with missing values, for example, if there isn't something found, if there isn't a match. You can do a right join, you can do an outer join. There's different ways of doing joins as well. The next parameter is on. So you can use the on parameter if the columns you want to do the match on have the same name, then you can use the on parameter. If they don't have the same name, which is, I think, most data sets, you can say left on, right on. And your data sets don't have to have the same names for you to perform a merge. So our left data frame is going to be the site. Our right one is going to be visited subset. And then we can say left on, we are joining on name, and right on site. And then just showing you the data frame at the end. So yes, so inner is the default way of how it's behaving. Yeah. So for all my examples, I'm just doing inner joins, but depending on what you need, you can do left, right, outer, et cetera, et cetera. The left on, right on is simply specifying on the site data frame, I'm using the name column as the key, and then on the visited subset data frame, I'm using the site column as the key. So that's what the left on, right on is doing. Yes, you can. I'm pretty sure I show you that. Do I show you that? I hope I show you that. Oh, I think I took that out. But yeah, you can. If you have multiple keys, like everything else in Python, if you have to give it multiple of something, surround it in a set of square brackets and then just comma delineate them. And it'll just do a multiple column match for you. I think I was so panicked on like trying to finish the material. There was like, I think they'll get the point after this. So just to show you what a many to one merge or one to many, so again, this depends on what your data set looks like. You can do, for example, this. I think this is actually one to many, but I'll just call this M. So another way you can specify merge is the DataFrame dot merge. So you don't have to say PD dot merge. I think under the hood, this just calls that function. So it's really the same exact function that's being called. So during this, so the left data frame is going to be the one that we called merge on, and then the right one is the one that's actually closer to the right-hand side of the screen. And this performs that merge. One of our data sets had a missing value, and so you can see that missing value getting propagated when you perform these merges. Just to show you what the Cartesian product looks like, I'm going to make two data frames. So you can make a data frame using a Python dictionary, so these set of curly brackets. And the way that works is the key becomes the column, so the column name, and then the values become that entire row of data. So before I'd specify the information row-wise. If you do it using dictionary, you specify the information column-wise. So this becomes a column called A1, and that column has 1, 1, 2, 2 in it. Oh, I just called this A. All right, 10, 20, 30, 40, 50. We have 2. A1 gets 1, 1, 2, 2, 3. Gets 100, 200, 300, 400, 500. Right. So this is our data frame 1. So you can see that if I actually, data frame 2 would be a little better. You can see that I specified this data frame using a dictionary. The key becomes the column name, and then the value becomes the contents of that column. And if you look at data frame 1 and data frame 2, you can see in column A, or this first column, there are duplicate values in both sets. So this is what could happen. So essentially I'm performing a many-to-many. There's duplicates on both sides. And so if I do df1.merge, and I merge it with df2, and the left is on A, and the right is on B. Oops. Oh, A1. One, you'll notice that I got a lot more rows back than what I had. And if you look, you'll see that data frame 1 had 110, 120, 130. Data frame 2 had 1, 100, 1, 200. So I end up with 1, 1, 10, 100, 1, 1, 10, 200, 1, 1, 20, 100. Why is it jumping? 1, 1, 20, 200, et cetera, et cetera. So it's creating every pairwise combination that's going on. So any questions about what's going on there? Just keep in mind that's something that could happen when you're performing a merge. So if you end up with like all of a sudden a million row data set, and you're like, where'd this come from? The two things I joined together weren't even close to that. This is probably what's going on. All right, last topic before first break. To prevent the Cartesian product. If you wanted one-to-one instead of many, I think you're gonna have to get rid of the duplicates, right? Yeah, is that right? That seems, yeah, that's a little. I think you're gonna have to get rid of duplicates because if you say left or like left join, it's still gonna keep all it does when you say keep everything on the left side or right side is make sure that no observations on the left data frame gets dropped.
Right. I was trying
Yeah.
to distinguish the syntax. So suppose you don't know whether you have duplicates or not, right?
Uh-huh.
It's not an uncommon situation.
Yeah. So the easiest way to tell if you do have duplicates is if your number of rows is greater than either one of those data sets that you started off with. So
Yeah,
that,
oh, you mean when you finish up?
yeah, when you finish. So after you do the join, if you end up with like a data set with 100 rows and another one with 50, and you end up with 5,000, or even 101, you'll know that,
That's a pretty good tip-off.
yeah, that's a very, yeah.
Yeah, but the more interesting situation is you have, one with 500 and one with 450, and you end up with one with 475. What's going on?
Oh, so if you end up with, oh, yeah. Yeah,
That's a good question.
that's something for you to do more data exploration on. I don't think there's anything that you can do in the actual merge call that will.
There's no like duplicate command or anything that'll search for duplicates.
I don't think so.
Pardon me?
Wait, wait, can you say that again? Mm-hmm. Oh, yeah. Like that. Yeah. So you can check to see if there are duplicates in your data. Yeah. Yeah. Another way would also like get a column and do a frequency count that I'll show you, and then if a count is like greater than 1, then you know it got duplicated. So, or you have duplicates, not it got duplicated. Yeah. All right. So, like I've promised, we've seen missing values, so now we're gonna just work with them for a little bit. This is a new notebook, so I'm going to have to import this stuff again. So the missing values actually come from NumPy, and there's 3 different ways that NumPy has missing defined. They're all exactly the same. It's NaN with capital N's, or all capitals, or all lowercase. So that doesn't matter if you want to insert missing values into your own data. You can import the missing value from NumPy and then just use that. The thing with missing values, this is probably a little faster type. Oops. Uh-oh. I don't think nope, I was not supposed to do that. They don't really equal anything, so they're not true, they're not false, and they're not equal to each other. So, and the reason behind that is a missing value could be anything. So it could be 3, it could be 5. You actually have no idea, so that's why they aren't equal to each other either, because there's no way to actually be certain that they are actually equal. They're just missing. You have no idea what it is. So if you actually need to test for missingness, there's a function called isNull, and if you give something that is missing, if you pass that into isNull, that's when it will become true. So if I give it something else that's not a null value or a missing value, it will return back false. Pretty sure that's also like the string dash. Yeah. So if it's as long as it's not NaN, it'll give you false. Yeah.
Quick question. So there's no real distinction between capital N, A, N, etc. It's not case sensitive, is really what's going on here.
It's not, but that's because I also imported all 3 versions of them.
I see.
Yeah.
I see. You have them explicitly.
Yeah. I just imported all of them just to show you guys that there's 3 ways that you can personally like type them. In the data frames, you'll see it printed out as NaN with capital N.
Right. So I was going to say you didn't import it specifically in the last module.
No. Yeah. So
in capital N
So pandas will represent missing like this, but if you want to use it within your own work, you can import any one of these. And I think if you use any one of these to assign into a data frame, it'll always print out like that. So depends on how far the shift key is away from your pinky.
Right. So you could conceivably, for example, merge two data frames. One had small case NaN, one had large case NaN, and they would show up as
They would be the
different
same.
values.
No, they're the same missingness. They will be the same. Like there's no distinction between these three at all. It's just how much you like your shift key. You'll probably see this a lot, like just in the around the internet, just because the data frames themselves always represent missing values as NaN with capital N's. So you end up doing what you see all the time. So I pretty much type it like this most of the time. I just showed you guys this just, you know, for completeness sake. All right. So where does missing value come from? So in our read CSV file, our function data. Uh-oh. Why is this not tab completing? Uh-oh. Where am I? I'm not supposed to be there. Why am I there? Oh. Oops. What should I do? Oh no, I can't. Can I do this? Yeah. Okay. All right. I'll move it later. Yes, you can run regular bash commands in these cells. That's sort of what IPython, which is what the stuff is running on, gives you. Okay, so visited. So when we loaded up our visited data set, there was a missing value in there. So one way missing value can come about is just in the actual raw data set that you're working with. If you look at read CSV, there are a few parameters like NA values. Where is this thing? pd.read CSV. Oh, there's a lot of these parameters. Okay. All right. One of these. NA values, yeah. So by default, it'll represent, if your data set has any value that is an empty string, it'll read in as a missing value. But you can change that if you change the NA values parameter to like 999 or 888. You can set that so that if you read your data set in, any value that says 999 or 888 or something will automatically get read in as a missing value or NaN. So there's different ways you can change that as well. There is also a parameter for if you want it to read the empty string as an empty string and not a missing value, you can change that in the read CSV call as well. So depending on what you need, it would either be the NA values parameter or some combination between that and the keep default NA parameter that you can use to change how your data set gets loaded in. The other way we saw missing values was when we performed a merge. So when we did our merge, because one of our data sets had a missing value that got propagated when we did our merge. Left on. So this is exactly what we went through before. just with a different example. Right, so in here, you'll see that one of our data sets had a missing value, and because this was a many-to-one merge, that missing value got duplicated in our data set. And so one thing that you would want to do is like count your missing values. So I'm changing data sets a lot, but here's another data set that's kind of fun. So here is a Ebola data set. So this is a data set about the 2014 West Africa Ebola outbreak. This was curated by at the time, a graduate student named Caitlin Rivers, who used to work he used to go to Virginia Tech with me, or not with me, before I entered. And she also gave a talk here at SciPy, I think 4 years ago as well, on EpiPy. So this was a data set that she ended up curating directly from various ministries of health that were reporting cases. And so just like any new data set that we load, we can look at the info of this, like I showed you during lesson 1. So this is a data frame. We have 122 rows and 18 columns. These are the column names on the left-hand side. And then here in the center, because there are missing values in our data, not every single one of those numbers is going to say 122. So this is one way you can get a sense of how much missing value or how much missing data you have. Just keep in mind, you actually have to subtract 122 from all these values to get the actual missing value count. This just tells you how many non-null values there are. And then on the right-hand side, the actual data type stored in there. And we'll go over data types in a little bit. But so floats are floating point numbers, ints are integer numbers. Object is Pandas' generic way of saying this is a string. All right. So if you have something with a lot of missing values, so let's say I'm looking at this case is Guinea, there is a function called value counts. Why is this not tab completing? So you can chain head to a series or a Pandas data frame if you want. So value counts will give you the counts of whatever is in there. And so if you're looking just for duplicates, what ends up happening when you do value counts is it sorts by the number of counts. The most frequent gets sorted to the top, right? So if you're looking for duplicates, this is probably another way you can just say, hey, I have duplicates in this data set, just because the first number is not a 1. Because this data set has like a fair amount of missing values, you can say drop NA equals false and I'll actually count how many missing values there are. And in this example, it shows up at the top, but that's only because there's 29 missing values in this column, and that's more than any other frequency count that we have in there. So just keep in mind, if you do value counts, it will just give you the count, yes, and it'll return it in descending order, but the number of missing values will not always be the first one up there. It just so happens that I just have the most common observation is missing. Yeah. So unique, there's a thing called unique that will give you back what are the unique values in there. There's n unique that will give you the count of how many unique values there are. And then value counts, I think I copied it. Value counts will, for each unique value, give you a tally. So those are the 3 differences. Like, what are the unique values, how many do you have, and then what are the tallies for each is what the difference between those 3 are. Oh, yeah. Oops. So this is the tally. I think that's spelled right. there's n unique, and then, yeah. So this gives you the tally. This gives you how many, and then this is the actual. I need to turn tap to click off. I thought I did. All right. Wait, can you say that again? Oh, yeah. Oh, I meant I need to turn tap to click off because my mouse is like bouncing off, bouncing around the screen and scrolling it. Yeah, yeah, it won't know when I'm trying to tab complete. If you want it to tab complete, you're gonna have to save each intermediate that you're doing, which is probably not a good idea. All right. Cool. All right. So the next thing I want to go over is how do you recode missing values? So that was the question of, let's say I have 88s and 99s and I just want to either turn them missing or actually that isn't the question that she had. Yeah, it was the opposite. Yeah, I'll show you how you can recode missing and then the other way around. All right. So we have our Ebola data set. So we have our missing values in here. So there is a function called fillNA. And if you give it something like 0, it will take every value in your data set. This works for a column as well, so I'm just applying this throughout the entire data frame. If you give it some value, in this case 0, it'll replace every NA value with 0. I'm pretty sure if I had said something like that, it would do that. So whatever you give it, it will turn all of those missing values into that value that you gave it. That's not always the best thing to do, depending on your use case. Scroll down. So there's other ways that you can do this. So there is a parameter called method. And so method, if you look up the actual documentation, there's like 2 ways. I think it's 2 ways. There's 2 ways that you can fill your missing values, but there's 4 different ways you can specify it. It's kind of weird. I don't remember all of them. Anyway, so you can forward fill your missing values, meaning that for a current missing value, it will take the last known value before it. So that's a forward fill. So let's look at our Ebola head. So let's say, look at this cases Guinea. We have this NA value. So if we do a forward fill, what it's going to do is keep looking back to the last known value and use that value to fill in its value. So if we want to do a forward fill, it's ffill. And if we look at the head of this, you'll see that this 276.90 got filled in with the last known value. You can also see that when you do a forward fill, if the column already begins with the missing value, it's going to stay missing because it has no idea what came before it to fill. So when you do a forward fill, you're pretty much guaranteed that the end of your data set will not have missing values, but the beginning you're not guaranteed to have non-missing values. And then the total opposite way of doing that is backfill, so bfill. So you can see that this 273.69 that got filled before got backfilled. So this starts looking from the bottom of the data set up. And you can see that the missing values at the beginning of our data frame now get filled. But that means that the other problem happens where the data at the end of your data frame ends up being missing. So if you actually need it to fill both ways, you're probably going to do a forward and backfill, and then you have to determine which one you want to do first. And then the last thing before break, and then I'll look up a few things while you're on break, is running calculations with missing values. So you can, for example, this case is Guinea does have missing values in it. So let me show you that this is actually. So because I never saved the forward backfill stuff back to a variable, so that never really got saved. So you can take the sum of a column even if it has missing values, right? So that's something that you can totally do. That is not the default behavior in R. But if you want to actually throw some kind of quote-unquote error when there is missing, there is a parameter called skip NA. And if there is a missing value in that column, sum will just give you back a missing value. So that is the default behavior in R, but in Pandas it just skips over them. So just be mindful when you are taking sums, you're not totally guaranteed that you do not have missing values in there. So yes, yeah. I don't really use NumPy, so yeah, I can't make that reference. But yeah, it's exactly how NumPy works, and I'm pretty sure it just calls NumPy. All right, cool. So be back at, yeah. Oh, question. Oh, yeah, so we'll go over that. I think in about a few more chapters. But if you have text in a column, so in Pandas, each column has to be the exact same type. So if you do have text in a column, even if it's a column of numbers, the entire column will be a object column, which is a string column. And so you wouldn't really be able to take a sum of all strings just because. So you actually have to do you actually have to convert the column into a numeric column, which I'll show you in a bit. But all right. Yes, so be back at 10:55. So that's like 10 minutes. Is that right? 9:55. Sorry. Just to backtrack a little bit, if you Google Pandas DataFrame or Pandas Series, the first link is going to be the official documentation for a data frame or a series. And this is because someone had mentioned, yes, I definitely misspoke. You shouldn't really think of each column as a Pandas series is not really a NumPy array. They're not exactly the same, mainly because the methods and all of that stuff are different. So a Pandas series is a one-dimensional array. Typically, it's a column in your data frame or a row. And if you scroll down, you can see everything that this series object can do. So the parts that say attributes, those are the things that don't need sets around brackets. So like IX or ILOC, you've noticed when I've used them, I just typed I.ILOC and then I just started subsetting it right away. I didn't have to use a set of round brackets. Below that are all the various methods. So why I was able to call mean on these functions was because there is a method called mean on a series object. So this entire list, if you ever have a question like, hey, I have this column, can this column do this? Take a look on the official documentation and you can say like mean and it does calculate the mean. So you don't always have to write something from scratch. Take a look at the documentation, it's pretty useful. And the same thing applies for data frames. So in the data frame stuff, you have, actually the series has this stuff too, I believe. Yeah, so all these to underscore methods, they're in a data frame or a series. The minute details you will have to check. But everything that a data frame or a series can do is listed here. So you definitely don't need to remember what can do what, um, especially if you were like, all right, so Dan got something, got a count. Like, what were the different ways to get counts? So you can look on this page for count and see all of the, if they label things or if you're doing your control F correctly, you can see like there's value counts or things like that. All right, so the next part of our pandas tutorial actually borrows very heavily from the R world. And it's this notion of tidy data. And Hadley Wickham has written a paper about this, which is also linked on the actual page. So you don't have to remember how I'm Googling this. But I want to do this. I'm not sure if I want to do this. Yeah. So he has this paper about tidy data. It's the examples are in R, but the concepts are, I'm going to show you what the concepts are in Python. And it's actually a very good read in terms of if you get a data set, especially if you're starting off with data processing or data analytics, what your first steps are in the data cleaning process, right? So far all I've done is work with relatively clean data. We did frequency counts, which is important. We looked at unique values to make sure there isn't anything too obscure. But when you actually need to start doing like quote unquote data munging, this paper is a pretty good read about what to expect. So actually I had the data sets loaded up, but I'll just use this paper as an example. It'll be less typing for everyone. All right, so he goes through some of the language about what makes data quote unquote clean. And so he has these two data sets. There are, for data set one, you have people's names, you have two different types of treatments, and then a value for their treatment, right? And then you can do a transpose on this data set and you get the same information. So you have treatments as your row identifiers and each individual person as its own column, and then their treatment value in there, right? So if you're trying to describe a data set, it's pretty ambiguous in terms of what is a column and what is a row. And so he tries to formalize those definitions. So when I say row, I mean Hadley describes it as a row is a single observation of data, and a column contains a variable in your data set. So how do we want to quote unquote make this data tidy or clean? We want each column should be a variable. So we should have a variable called person, a variable called treatment, and a variable called result. Each of those variables are separate columns. And then each row becomes a single observational unit. So we have a person with a treatment and a result, right? And so this is what Hadley would describe. This is a tidy or clean data set. But this isn't this isn't a table that you would put in a paper, right? Just because it's a little hard to figure out, compare different treatments. But when you are cleaning data, especially when it's data for analysis, this is a pretty good target to clean your data to, because then you can say, group by each treatment, give me an average result, right? So it becomes very easy to work with when you're trying to do data tasks. Also, when you have a data that is quote unquote tidy or clean in this format, you can very easily switch to any of those other types. So this process of getting your data tidy also will fix a lot of other problems in your data set along the way. And those are very common data set manipulation tasks that he describes in this paper. So what is tidy data? He says that in tidy data, each variable forms a column, each observation forms a row, and then this last bit I'll describe, but we sort of already dealt with this. But each type of observational unit forms a table. Most of the time when you are doing data analytics, you violate this last principle just because you're merging and combining data sets. So in our survey data, each individual table was a separate observational unit. Right? We had a table about a person, we had a table of the readings, but when you actually perform data analysis, you you merge it all together. So so this last bit is really more on the how do you store data and how do you give data to other people, not really a use for data analysis. So he goes on to describe in this paper, here are some very common problems that you have with your data. And what I ended up doing is, you know, the data for this paper and the tidyr package are all on GitHub. So I essentially just downloaded those and uploaded that in our tutorial. And so I'm going to be going through this paper with you guys, but using Python syntax instead of R. And so we'll go over these very common, but these aren't, this isn't the final list, but you can have columns that are headers. Column headers are values, not variable names. So in the example before, if you had, you know, John Doe as one column, Jane Doe as another column, you have this column headers are values. They're not really variable names. So that's what that's referring to. And then I think the rest I'll just describe as you see the various data sets, because it's much easier to describe them that way. But I would highly recommend reading this paper just to get you thinking about what you have to do when you start processing and cleaning your data. Okay. Where does this put me? All right, this puts me in somewhere I don't want to be. Is this 4? 4. Great. All right. Oh, sorry. Last thing. Someone over there had mentioned how do you replace all the 88s or 99s with a missing value. So there is a method called replace. Replace takes a parameter, so to replace. So in here, you give it all the values you want to replace it with something, and then the value you want to replace it with. So in this case, I'm replacing it with a missing value, but you can replace it with an empty string if you want, or a 0 if you want as well. So that's one way to do it. Just be a little bit mindful, because I've done this in my code where I've replaced an entire data set with 88s and 99s to NaN, because that's very common in health data sets. You might have a column that's like ID numbers that will be from 0 to something. And if you do this, you will replace the 88 or 99 ID number with a missing value. So just keep that in mind. That's sort of the nice thing when you start doing analytics in a programming language of some sort, is because I was able to find that mistake. Had I just done a find and replace in Excel before processing my data, that would have been a much, much harder error to fix. So you can replace a value with whatever value you want. Just be mindful of what's in each column. So we're gonna load our library again, because this, at least I'm working in a new notebook. There is a data set called Pew for the Pew Research Center, and this all comes from that tidy data / tidyr package. So here's our data set. This is if you're very used to looking at academic papers, this is probably table 1 of some paper, right? You have just some kind of demographic and count of some sort, just to give a high-level overview of what's in your data set. Again, tidying your data is different from presenting your data. But if your data is tidy, you can transform it very quickly into a format that is easily presentable. So this, from a data analytics point of view, is not a clean data set, because yes, we have a column called religion, and that's listed, but these columns right here they're actually values. They're not they're not individual variables, right? So what we would want is a column variable that says income range and then the count there, right? Some rule of thumb is you'll know that your data isn't tidy if you can't do like some kind of group by aggregate, right? So I can't say, hey, find me for each group or for each income bracket, give me the average number of whatever religion, right? So that's some kind of mental thing you can say to yourself to see if something is tidy or not. All right. So what we want to do in this case is our religion column, that's fine. We can leave that alone. But what we would want is for all of these, for all of the other columns, we want to essentially, the Excel term is do a pivot table, pivot them into a single column, and then have the values here be another column for values. So how do we do that? There is a function in Pandas called melt. If you are using Hadley's plyr package in R, this is exactly the same verb that's being used. If you are using the tidyr package, it's called gather. So how does melt work? So the first parameter in melt is, in the documentation says frame, so this is our data set. So pew is our data set. The next thing is the ID vars. So this is, I like to think of ID vars as this is the column that I want to keep fixed. I'm not trying to pivot this column at all. So this ID vars, in our case, is going to be religion. Did I spell that right? That looks totally wrong. All right. Okay. And then just for, because someone's going to ask, what if you want more? Put it in square brackets. So if we run this, this will pivot our entire data set into something quote unquote tidy. It might not be as easy to get a high level overview of it, but this is in a shape that's much better for general data analytics. So we have our religion column, which is what we want. We have our variable that got all of those columns got pivoted down, and it got a default name of variable. So we have our under 10K, we have our 10 to 20K, greater than 50K, and then don't know refused, right? And then the body of the table became another column. By default, that column gets a name called value. Right, so I'm going to copy this row again. But if you're already going to do this data processing step, you might as well make these column names kind of useful. You are cleaning data, so you should probably have a self-explanatory data set if you can. So in here, there's a few other parameters that we can use. So there is the so there's another parameter called value vars. So what ends up happening is whatever you don't specify as ID vars will be passed into value vars, and those are the columns that will get pivoted down. So you could, in this process, do some kind of subsetting of your data in one step as well, but typically depending on what's easier, to specify the columns you want to keep fixed and then pivot everything else, or you can use some combination of the two. But there is another parameter called var name. And so this is when those columns get pivoted down by default, you see that it gave it a variable called variable, or a name called variable. So that parameter lets you change that. So we can call this income. And then the same for value name. By default, it got a column name called value, so we can say count. And if we do this, you can see that those two lines, or those two parameters that we added to the function, all it did was rename our pivoted or our melted data frame. All right. So what if we want to keep multiple columns fixed? So there's another data set in here. Called Billboard. And this has, for a particular year, an artist, a track name, there is the length of the song, the date this song got entered into a Billboard ranking, and then for that particular year, so this goes from week 1 to week 52, that particular song's ranking. Right, so this is sort of the same issue we had before. This week is really a variable, but it's being shown as separate columns, right? But again, this is some balance between, a data set that is for you very easy to visualize versus a data set that's made for doing kind of data analytics tasks, right? So in this set, and the way the data is shaped right now is for any given song, you can very easily just scroll across. Why does it go to 76? Okay, I don't know why it goes to 76. You can easily glance across and see how a particular song changes and ranks over time, right? So that's why this data set is in its current shape. But if you think about it from an analytics point of view, you won't be able to say, like, does a certain week number relate to the actual ranking, right? That's not, you can't really fit a model the way the data is in its current shape. So if we wanted to melt this data set, it is pd.melt. So this is exactly the same thing as before, except if we wanted multiple ID vars. So here's an example where it's much easier to specify 5 columns versus 72 columns, right? So here we want to keep year, artist, track, time, date entered the same, and then pivot the rest of the columns down. So here we specify year, artist, time, date, entered. This is also how you know this is an R data set because there is a period in our variable name. Value name is equal to rank. So what are we going to name these columns? So we can say var name is equal to week. Did I spell this wrong? Yes. All right, there we go. Wait, hold on, give me a second. This looks kind of weird. Did I forget something? Year, artist, time. Oh, track. All right. Sorry. What was your question? So that wouldn't make sense on how this function works because what it's doing is it's specifying all the columns you didn't specify, and that's going to be its own column. So you really only have one column that's getting created, so you wouldn't be able to specify multiple variable names. That's a separate problem we're going to address later on. That's another data cleaning issue, I think. And if I don't cover that, then let me know. Yeah. All right. So, all right, cool. Any questions? So if you have multiple columns that you want to keep static and pivot everything else, this is one way you can do that. All right. All right. So here's another data set that has a different problem. So here's a TB data set. If you ever look at health data, this is actually very common in how health data is reported. And the problem here is multiple variables are stored in a single column. We have a given country, year, and then over here we have a column that represents males 0 to 4, males 5 to 14, males 0 to 14, males 15 to 24, males 25 to 34, and then we have the same thing for females 35 to 44, et cetera, et cetera. This is for females unknown. This is females 65 and above, et cetera, et cetera. So that's a problem. We have a column that is now storing 2 bits of information, and we need to separate that somehow, because although this is okay for maybe a table in a paper, it's actually a huge table, so this probably wouldn't be in a paper to begin with. But you know, we have to do something about that, because we can't say how, like, what is the average, you know, TB count across males, right? Because it's all put together in this in a column. Yes. All right. How would data end up being like this? You know, this is probably very easy if you're entering data manually in a spreadsheet. Like during the data collection process, this is probably a format that made the most sense for whoever was collecting it, right? So there's nothing actually wrong with this data set. It actually has some kind of purpose to it. It just, you as an analyst need to deal with making this a little more useful for your analytics. And then again, once you clean this up, you can always come back to this data set. And another data set that has the same exact problem was our Ebola data set. Right, so our Ebola data set had exactly the same problem. We had whether this was a case or a death count, and then what country that was associated with for a given date. And the day is, I think it starts from like when the first outbreak happened. So there's like a global count versus the actual day, because different countries had an outbreak at different times. So there's I guess, a number that's counting from the very first outbreak that happened in West Africa versus the actual date. And that's also why there's a lot of missing values in this data set. All right, so how do we clean something? I'll just go through the Ebola data set because it's a little more complicated, so hopefully some knowledge will transfer to the other one. All right, so what's the first thing that we have to do? Well, we have all of these columns, so the first step that we're going to have to do is pivot them down. They'll get us one step closer into having a column that is the, what did I end up calling them? The status, whether it's a case or a death, and then a country, right? So step one, let's melt our data, and then hopefully it gets us somewhere closer. So Ebola melt is pd.melt. Our data frame is going to be our Ebola data set. Our ID vars are going to be date and day. So it is case sensitive. So I do have capital letters there. The value name is going to be count. And then my var name is going to be, I called it case, what did I call this? Status, country, oh, I don't know. I called it CD count, country. I don't remember why I called it CD. Oh, case death. That's why I called it country. All right. So if we look at this, that's one step closer to what we have in a clean data set. We have our cases and our country and then account. So it's not fully clean yet, but this looks like something that we can probably deal with. And it's one step closer. Right? So how do we deal with this problem now? So the column that we want is this Ebola melt. So what is the column that we're looking for? Is CD country. So that's the column that we have. If you want to take a column and treat it as a string, like a vector of strings, there is a attribute called str that takes whatever column and converts it into a string. So you can do regular Python string methods on them, right? And the thing that we're going to be using is you can actually use a built-in Python method called string.split to split a string by a certain character, right? So this is a data set that's kind of, it's at least in some useful or easy to clean format because we have a status on the left, a country on the right, and a thing separating the two is a single underscore. So we can use that pattern to break up this column. And so this ends up going into the realm of doing string manipulation, which is going to be pretty much most of your data cleaning tasks is going to be working with strings, just because it's probably the easiest way to collect data. It's just have unstructured text. So all right, so we have the string. If you think about what types of string methods are available in Python, so you can look up Python string methods, common string operations. You can go to whatever version you're on. Ooh, yeah, so there's this string.split. And so this is essentially the function that we'll be using. For example, we have 1, 2, 3. If we say dot split, we get a list back 1, 2, 3 that's split by the comma, right? So that's exactly what we're going to be doing, but in our case, instead of the comma, we're going to be using a underscore. So we're going to say string.split, and then we're going to split by the underscore, right? And so that gives us something closer to what we want. This looks like a list, so if we get the type of our first element, for example, it's a list, so that's good. We got a list back. We can work with lists. And then the first element of the list is this cases or def status, and then the second element of the list is the country.
The list is a fancy name for a vector, or there's some special properties of list?
So a list is a regular Python built-in data type, and it's a container that stores an arbitrary number or set of things, or it's not a set. It just stores an arbitrary set of like things.
It's just a 1-by-1 array, or a 1-by-n array?
I wouldn't call it an array only because you can't say. How do I phrase this? Yeah. Yeah, it can be heterogeneous. It's just a generic container to store stuff. It's not an array because it's heterogeneous, and it's not an array because you can't, without doing other things, perform like vectorized operations on it. You can't say like take the sum of a list, and then, or you can't say take a list and +1, and each element will element by element add 1 to itself. So. So this list is a regular Python list. That's a pure Python list. I have a bunch of lists together, and that's in a Pandas series. So this is a Pandas series where each element in the series is a Python list. So that's what we ended up with. All right. So I'm going to save this to a variable because this is something that we want to keep to continue working with. So if we want to get a particular index out of a list, or if we have a series or some kind of array, and each element in that series is a list, and we want to, for example, get all of the index zeros out of this at once. we can say, hey, use this str attribute, use this get method, and we can use this to say get the first element out of, in this array, just get the first element of each list. And we can say get 1 and get the second element out of this list. And so we can use that to advantage by saying, let's look at our status values is equal to this, and then our country values is the same thing, but it's the second argument, right? So if we look at status values, this is all of the just the statuses, and if we look at countries, it's just the countries. So that's much better. We totally separated out that column into the various parts that we need. The last part that we want to do is assign it back to our data frame. So how do we assign a new column to our data frame? We can say square brackets, and directly in our square brackets, create a new column and assign that, assign the new columns directly there. And we want to do this for status and country. So we can say, give it the status values, give country the country values. Now, if we look at that, we've completely cleaned out that column. We have a separate column for cases and a separate column for countries. Yeah.
So when I look at what you did there with SciPy equals r split str get, I would have just assumed you would have just said get, and I tried it, and it gives me, instead it gives me the first element. So what is this called a str here?
Does that give you the same thing?
It doesn't. It gives you the first row.
So what ends up happening, I think, you need this here to make sure it acts in a vectorized manner. So if you get, it's just going to end up pulling the first one, but it needs some way to say, hey, I need to do this element for each element, not just the first element. That's my explanation. You can't, yeah. So that's generally what's happening, and that's just to go into the next step of, you can actually do this all in like a fewer steps. So we can say, variable split is our same thing that we did before. But now, if there is a parameter called expand, and if we set that to true, what we end up getting back is, instead of a series where each element of a series is a list, we get back a data frame that's already broken up for us. And what's going on behind the hood is, if you give pd.dataframe a bunch of lists, it will create a row for each list that you give it. So that's kind of what's going on behind the scenes. So now that we have this data frame, let's kind of clean this up a little bit. So we can say columns. We can rename the columns here for status 1, country 1. Right, so all we did was rename this new data frame. And just like the example from the data assembly chapter, we can concatenate these two things together. So we can say our final Ebola clean is going to be pd.concat. We give it our, which one? Which data set was this? Oh, Ebola melt. Ebola melt, and then this variable split. Right. So that's another way you could have done that, or these nans. Uh-oh. Oh, whoops. Axis is 1. Yeah, I meant to do that concatenate the columns, not rows. All right. Okay. So another type of data cleaning problem, I think it addresses your question earlier. So there is a data set called weather. And so this is the example of variables are in both rows and columns of our data. So how do you know that this is a problem? First of all, if you ever end up with a data set where like pretty much two or more rows are exactly the same minus like a few details, a few changes, that's one litmus test that you can, that's something that will give away that this is the problem that you have. More specifically, we have this element column. There's a T max and T min, and then a bunch of days. So the first thing we're going to have to address is these days should probably be in its own column called day. The values here should probably be in its own column called value. But the problem is this T min, T max. What we should have is a separate column called temperature min and a temperature max, right? In our example here, those values are in the same column, and that's why we end up with a bunch of duplicates in our data set. So for example, look here, we have ID, year, month duplicated, and the only difference is we have a T min, a T max, so 27.3 for day 2, and then a T min, 14.4 for day 2, right? So there's a lot of duplicates going on in this data set, and so this is a problem that we're going to have to address. So how do we fix this? Well, the first step is going to be melt. So we'll do that first. ID vars is equal to, so this is ID, year, month, and then first we're going to keep element. Say again? Oh, there we go. Thanks. So our var name is going to be day. Our value name is going to be temp. So if we look at that, all right, cool. One step closer to what we want. Now you'll definitely see like the amount of duplicates that we have for each day. Pretty much everything except element and temp is going to be duplicated in our data set. So the last step, which is pretty much the opposite of melt, is how do you pivot up a column? So what we want is we want to take each unique value of element and turn that into a separate column. So our final data set will have an ID, year, month, day, temp, a T max, and a T min column. So the way we do that is we take our data frame. There is a so there is a function called pivot table. So just to show you the different ways you can do these syntaxes, whether all of our data frames also you can call melt directly on the data frame, so you don't have to say pd.melt weather. You can say weather.melt, and it's doing the same thing. You can say pd.pivot table. In my case, I will show you. I will use this syntax. So instead of pd.pivot table, I'm running dataframe.pivot table. All it does is it lets you specify this thing and without it in the actual function call. All right. So how does this work? You end up doing the very similar syntax or concept. You have an index. So that index, those refer to the columns that you want to keep the same. So when we pivot up our element column, we want the ID, year, month, day to stay exactly where they are. We will pivot up the element column, so that's what the columns parameter is for, which column you want to pivot. And then as you're pivoting, those are going to be creating new columns, so you have to specify the column you want to populate those new columns with. And so you use there is oh, I guess it's not showing you here. There is a values parameter, and that's how you specify that parameter there. So we have an index, which is the columns that we want to keep the same, which is ID, year, month, day. The columns is going to be element, and then the values is going to be temp. And then I will just print the head of this. All right. Let's do a little more. All right, so that's pretty much what we wanted. We have our ID for a given ID, month, year, day. We have a tmax and a tmin, and then that value will contain whatever temp was before. So maybe this will be a little, yeah. So for a given set of days, there's a tmax of 27.8 and a tmin of 10.5. And just like before, what I like to do is flatten our data set. So I will say reset index. So I get something that's a little more like a regular data frame that I'm used to looking at. Cool. Any questions? So pretty much between melting and pivoting, you're going to end up doing a lot of your data cleaning processes just by pivoting, cleaning, and then repivoting back. So it's a very important skill. And if you can see your data cleaning pipeline using this, it'll probably make your life a little bit easier. All right, so any questions? That answer your question about the data problem? Mm-hmm. Mm-hmm. Multiple variables. I think I'm gonna have you after like draw this out on the next break. Yeah. Oh yeah. So this you're not totally done cleaning this data set yet because you need to get rid of this d and then turn that into an integer. That's some combination of what we did with the Ebola data set where you did a split instead of doing a string split, you're doing a string slice and you're just saying start from the second value and go to the end, if that makes sense. So you have a thing like D10, so that's like your string. So you'll end up doing something along the lines of start from the first and go to the end. And so you do a data cleaning step, something like that, and then turn that into an integer. So yeah, it's not fully cleaned yet because you really can't use this this day column yet because it has this string. It's really a string, not a number, but I'll go over I'll go over like data types next, and then how you can write your own functions to clean data. Yeah. Oh yeah. So what's cool about the pivot table function? So there is a function called pivot and then pivot table. They do almost the same thing. Um, what pivot table allows you to do is if there are duplicates that happen when you do this pivot, it allows you to specify an aggregation function. So by default, it'll take the mean, but you can change it to min, max, something, something. So if you try to do something that does have duplicates after you do a pivot, and you use the regular pivot function, it'll give you an error saying that I have no idea how you want to reconcile these multiple values. So I typically end up just using the pivot table function just because it can handle multiple values and calculate an average by default. I don't think so. Because what ends up happening after a pivot is a single cell, and you can't put 3 cells in a single cell. But if you need to do that, there's other methods which I'll go over. Essentially, you'll have to write your own function to do these calculations. Right. Cool. Right. Okay. Actually, starting to feel time pressure. All right. Next up, data. Hopefully, this one will be quick. So the next thing I want to talk about is data types. We will be using data from the Seaborn library. Seaborn is a plotting library in Python. I personally like it because it looks more like how I can plot in R, and that's really only it. But it also comes with a bunch of data sets that are pretty cool. So, well, they're not cool if you've been doing data analytics for a while because they're pretty much used to death. So we can say sns.load dataset, and there is a tips dataset. And so essentially this is a data set for a given total bill. What was the tip given some kind of characteristics of the table? Yes, it doesn't make 100% amount of sense because you can have a size of like 6 people but still have 1 gender associated with it. So I don't really know what's going on there. But how do you look at data types? So there's the info thing that we've been looking for, and the last column here are the data types for each group. You'll see a new one here called category. This is, I think, from like Pandas 0.16 or something. They added the category data type, so this is like an R factor. And essentially, under the hood, these categories, they look like strings, but under the hood, they're coded as some kind of like integer or something. And it's really, it makes doing analytics later on a little easier because you have this notion of a dummy variable. Oh, do you need me to go up? You have this notion of a dummy variable, and because it's under the hood stored as like an integer or something, it can make larger data sets smaller in memory because you have the string DINNER, but it's really getting coded as 1. So if you have 1,000,000 of these, it will save a great deal amount of space in memory.
Question.
Yep.
So if you wanted to, so that means many situations you'll have a variable as a categorical variable enter this text.
Mm-hmm.
You want to convert it into numerical coding like you're describing with the internal format. This data set comes pre-coded.
Yes.
Obviously going to be some kind of function code.
Yeah. Yeah. So I think the function is pd.categorical, and if you give it a column, it'll turn it into a categorical column. Yeah, yeah. So that's that check. So we're gonna go over how you convert data types. So that's how you would convert a column into a categorical data type. But most of the time, especially I prefer, if you can, work with strings and not categories, because dealing with a category, essentially, there's like some other layer you have to deal with, because there's like this mapping that's going on. So when you can't really just, do like string split and string replace and just assume that the category got recoded. So there's a few hoops that I'm not going to go over, but categories, when you actually are working with them in your data cleaning process, I would almost say convert it into a string and your life will be easier. So that's what I'm going to show you, is how you just convert things into a string. And then, typically when you're like preparing for data analytics, a lot of like uh, stats models or scikit-learn, they can handle these categorical data types. So when you're done cleaning with everything, that's when you would use pd.categorical. So how do you change data types? So let's take this tips data set, and we'll create a total bill string. And that's going to be tips. That's going to take this total bill column. And the way you essentially recode a variable or a column to a different type, there is a function called as type, and you give it the type that you want. So str is Python's designation on converting it into a string. So if you wanted to convert it into a floating point number, you can say float. Right? So you can't really see when it's printed, but this column, if we look at the info, is now an object, which is how Python or Pandas calls string objects, or strings. So you can use as.type to convert anything from one type to another. When you're working with numeric types, there's, I think this answers someone else's question here. So let's say tips sub miss equals tips.head. So I'm just going to take the first 10 rows of our tips data set, and I am going to not randomly, set the total bill to the string missing. Right. Yeah. So this warning is essentially saying that I'm making a copy. I know I'm making a copy, but this is just a warning telling you that you might not be doing what you're expecting to do, but I'm totally expecting. I know I'm doing in this example. So I have this data set or this subset, and I converted a few of these into the character string missing. So what happens if we look at info, or another way we can look at our types is just running d types, is our total bill is now an object, right? That makes sense because it used to be all floating point numbers, but because we had inserted strings into it, it has to convert everything into the lowest common denominator, which is a string, right? There's no way to convert missing into a floating point number. And because each column has to be the same type, that's when we had created, when I had ran this line right here, it had coerced everything back to a string. So if we wanted to, we could have said something like get the total bill and do as type it was a float. That's going to create an error because it has no idea how to convert missing into a floating point number. So if that's the case, so in R, like that's kind of nice. Like if you say, hey, as dot numeric into something, it will just automatically coerce everything into an NA if it doesn't find it. So Pandas has something that's like that. There is a pd.toNumeric function. So if we run that, we get the same mistake or same error, and it's going to say unable to parse missing. I have no idea what to do with missing, and that's because if we look at toNumeric, there is a parameter called errors, and by default, it's set to raise. So if it tries to convert something to a numeric, and if it encounters a mistake or something it can't convert to a numeric number, it's going to give you this value error. That's what is being raised. But there's a few other ways you can change this behavior. So you can say errors is equal to ignore, in which case it will just ignore it. But that kind of doesn't help because your D type is still an object, but at least it didn't give an error. And then the last thing that you can give it is coerce, which will force everything into a number, and if it can't, it'll give you an NaN value. So this is the default behavior in R. Right? So if you have a column that you know is only supposed to have numeric values, and for some weird reason there's MISSING or something, you can say to numeric and just convert the whole thing into a floating point number, and everything else that couldn't convert will get blanked out to a NaN missing value. Like incorrectly? Yeah. That's not like a British spelling, right? Maybe it's such a common spelling mistake. Anyway, yeah. It doesn't. It'll just go through, but it's not giving you an error. I don't know if it's useful. It's just in the documentation that's provided. I can see it being useful because you kind of don't want your code to just break if you're giving it to someone else. So yeah, so ignore will just silently let it go, but the type never got changed. It's spelled two ways, right? Okay. I know I tend to in general mix my or add C's and S's like on a whim to like things I type. So, oh, okay. Yeah, I don't know. Good for them. Catching my spelling mistakes. Okay, so can I do, how much is left? Group by, all right, so I'm pretty sure I have enough time. All right. All right, so then last thing second to last thing, is this notion of apply. So this is what happens if you're pivoting tables, that's not enough to clean your data, or for each row of your data, you want to perform a more complex calculation other than adding two columns or calculating the mean of the row or something. Something like calculating a z-score is something that is a little more complicated to calculate, so you might have to end up writing your own function for. So just to show you how apply works, I'm going to be using a few very simple examples, but then we should have enough time to actually do a full-blown example at the end. So let's write, so the first thing is, here's a quick few seconds on how to write a function. You say def, the name of your function, you indent 4 spaces, and then you have your function code, and if you have a empty function, you just have pass. So this is a function that does absolutely nothing. But let's write a function that's a little bit more useful. So that was it. That's how you write a function. That's the entire tutorial on functions. So if you want to write a function that's a little bit more useful, like square a number, you can say squares a given value. So you can write a doc string because that's good to have. All this is doing is returning x and raising it to the second power. And if we want to use this, we can say my square 2, my square 4, and it'll just square that number back for us. If you want a function that takes 2 parameters, that says calculates the average between two numbers. That's x plus y. So this is the difference between Python 2 and 3. If you're in Python 2, this should be 2.0. That's it. I'll just write that there. And you can say, what's the average between 10 and 20? And it should give you 15, right? So how does this play into the world of apply? Typically, let's say, for example, you want to perform a calculation on each row of your data or each column of your data. If you are coming from, depending on where your programming background is, you might say, hey, I'm going to iterate through rows or columns. Let's write a for loop. Don't do that. It's typically when you're working with data sets, that's probably the slowest thing that you can do is write a for loop to iteratively run a calculation across columns or rows, especially if it's each column is completely independent. Each calculation is independent from another, right? So that's where you run and apply. This is more of like a functional paradigm kind of thing where you write a function and then that function gets quote unquote applied across every single column or every single row essentially at the same time. So I'm going to make up a data set. So I'm going to create a data frame. It's going to be a simple data frame. It's going to say A is 10, 20, 30, and then column B is going to be 20, 30, 40, right? So not a fancy data set at all. If, for example, we wanted to really calculate the square of column A, I could have said like, hey, take column A and square it. This is what I meant by a vectorized, something that's like a vector versus a list. You can't do that to a list, but because the series is a vector, it knows how to handle, hey, you told me to square it, so I'll square each element, element by element. So how do we do apply? So we have this function that we just wrote. That says my square. It takes a single value and squares it. So how do we do this? Well, we have this vector of single values. So this is just 10, 20, 30. If we want to apply a function that we wrote, we say dot apply. So we're using the apply method. And we give this method the function that we want, right? So these two are doing exactly the same thing, but this function is a function that we created on our own. So this could be any kind of crazy function that does some kind of calculation for a given number. All right, cool. So what about this other example? We had this average 2 that takes two values, x and y. So can we use this to say, for each row, calculate the average? So give it 10, 20, this should be 15, 20, 30 should be 25, 30, 40 should be 35. I am skipping a step, but okay, it's fine. So that presents a problem or something else you have to think about. Because we're working on a data frame, there's two different ways we can specify apply, right? Do we want something to work row by row or column by column? So just to see what happens when we run and apply on a data frame, I'm going to say write a function that all it does is it prints whatever you give it, right? So whatever you give it, it just prints. It's simply a print statement. So let's say I run df.apply and I give it this print me function. So you can see it printed some things for us. So it printed 10, 20, 30, and then it printed 20, 30, 40. So you can see when we ran apply and we look at our original data frame, it printed 10, 20, 30, and then 20, 30, 40. So apply on a data frame by default is operating on a column by column basis. The results are none because our function doesn't actually return anything. So that's why we have none, none. So the other way, at least in this example, we know it's going column by column is because the return has two none values and we only have two columns. So by default, apply will work column by column. Right. So this is pretty much exactly the same thing as df A and df B, right? So it did something on column A, it did something on column B. So let's write another function. Average 3 takes x, y, and z. So this calculates the average between three numbers. So this is x plus y plus z and divides it by 3. And so let's say now we run df.apply. We have this average by 3. Thank you. We're running this. So we want to calculate for each column, we want to calculate the average, right? So we have 10, 20, 30. The average should be 20. 20, 30, 40. The average should be 30. So we run this. That's going to be a problem. And that's a problem because what actually happens when you run an apply is the entire row, or in this example, the entire column, gets passed into the first argument of the function. So what really got passed into this function was 10, 20, 30, the series, all got passed into the variable x. Nothing got passed into y and z, which is why the error is going to say, I'm missing two things, right? So if you're going to write an apply function, what typically is going to happen, or the easiest way to fix it, is you take your function, you make it so it takes one parameter because the entire row or the entire column is going to be passed in. So I'm going to say the entire column is going to be passed in. And then inside this, because it's the entire series, you can subset it just like before. So x is column element 0, y is column element 1, z is column element 2. And then if we say df.apply, we can say average 3, and then that will work. So that's actually one of the most confusing things when I first started working with applies is like, I wrote this function, why doesn't it work? It's because, yes, when you write your function like I did before, it's very easy to test. You give it 3 inputs, it gives you your results. When you want to use it for an apply, what actually ends up happening is the entire axis, or in this case, the entire column, all gets passed into the first argument. So you have to actually change how your function is written if you want to use it as an apply. That is a good question. X plus y plus z. That's why you unit test. All right. So if we wanted to do something on a row by row basis, we can say df.apply. Right now, our function won't actually work. So if I say average 3 col, whoops. If we want it to work on a row by row basis, we can say axis by default is to 0, so that means work on columns. But if we say axis is 1, this will work on rows. But this doesn't make any sense on a row by row basis because we're doing x plus y plus z. There's only 2 values in here, so our error is going to be something like index out of bounds, right? We're trying to get a third element that doesn't exist. So how do we fix this? Well, we can rewrite our function that says average 2. This now takes some kind of row, and now we're doing row 0 and row 1, and we're just doing x, y. Then we can say df.apply average 2, axis is 1, and then that will work on a... Yes. Yeah. So that's how you can write an apply function that operates row-wise or column-wise. All right. So how do we, so that's generally what's going on. So let's use an actual data set. Import Seaborn as SNS. There's a Titanic dataset. Load. Oh, load dataset. Uh-oh. Uh-oh. Load. Oh, dataset. All right, so here's a Titanic, the dataset of the famous Titanic, of whether some individual survived, yes or no, what their gender was, what their age was, some other stuff about the type of ticket that they bought, and whether or not they traveled alone or not. So let's look at the info of this. So you can, again, I'm not going to show you how you can do string parsing. You can do really complicated string manipulations, write it in an apply function. That's something that you can do. But I am going to show you how you can, for example, get frequency count of missing values, or what proportion of a row or column has missing values, or what proportion of a row is complete. So when you end up working with pandas, because so many operations are going to be vectorized that work on arrays, you're probably going to end up loading numpy as well, just because numpy functions work on arrays. So you don't have to write these vectorized functions yourself. So I'm going to write 3 functions. First is going to count the number of missing values. Next, I'm going to count the proportion of missing values. And the last one is give you the proportion of complete values. This is probably something that you will end up doing when you're working with a newer data set. So count missing. We're going to get a vector of some sort. I'm going to forego the docstring. So we're going to get how many we're going to get a vector of whether or not an element is missing, like NaN missing. So we have is null. We're going to give it the vector that we got. And then one thing that you can do is trues evaluate to like a 1 and false evaluates to a 0. So if you take the sum of a Boolean vector, that will give you how many true values there are. So that's what we are going to be doing. So this is a vector that gives me a vector of true false values of whether it's NaN missing, and then I'm summing it to get the total number of missing values. I'm going to write another function, is proportion of missing. That takes a vector. And a proportion has a numerator, so the numerator is exactly this count missing function that we got before. And the denominator is the how many elements there are in that vector. And then the proportion is the numerator divided by the denominator. And then the last thing is this is also a lesson in functions and how you can reuse functions that you've built, so you don't have to keep calculating the same thing over and over again. The last thing is proportion of complete, which is really the same thing. We got the proportion of missing, so it's 1 minus whatever the proportion of missing was. All right, so now let's actually use these functions on our data set. So Titanic. So we can say count missing. Oops. Uh-oh, what's going on? No module sum. Oh, this is NP. All right. So what did this do? So this went column by column and ran our count missing function. So we can see that age has 177 missing values, embarked has 2 missing values, and deck has 688, and where the person embarked from has 2. Right, and then just as sort of like an aside, you should always, if you are working with missing values, you should really make sure that those values are like actually missing at random. There shouldn't be a pattern in your missing values. So one way you can check is use this pd.null. Let's say embark town. Is null. Yeah. So remember, Loc has a comma. To the left is how you are subsetting the rows, and the right is how you're getting the columns. So I'm getting all of the columns, hence this colon. And then the rows is I'm taking this embark town column and seeing if it is null. If it is, return me those columns back. And so that's how this is. Working. And so, when you're working with missing variables, it's very important that you end up looking at what's actually missing, because you could end up with a data set that just so happens that like 98% of your male population is just all missing, and whatever model you're going to fit is not going to make any sense. Right. So this is all of the rows in our Titanic data set such that the embark town value is missing. So that's all it's saying. I'm not trying to make any inference off of this. Oh, this is the row number, or the row index. Yeah, so we only have 2 missing values in embark town. Yeah. Oh, this isn't the entire data set. This is just in this one column. Yeah. So this one column has 2 missing values, and that's what they are. I could show you this one with 688 rows, but that just becomes, it's not going to show up on the screen. So that's essentially why I picked that variable. All right, so we can do the same thing because our function is vectorized, and it's vectorized because we ran MP sum, so it can take any vector. So we can take our Titanic apply, and we can change the axis to 1, and this will give us, for each row, how many missing values there are. Right, so the first row has 1 missing value, the third one has 1 missing value, index number 5 has 2 missing values, etc., etc. What you can do is then say value counts, and you can say here 549 of our rows have 1 missing value. 182 of our rows don't have any missing values, and 160 of our rows have 2 missing values. Right. And so you can use this, substitute any of the other functions that we wrote. So we can say proportion complete, and here are the proportion of complete values. So when we don't have any, that's 100%. When we have 1, it's 93.3% or 86.6%. All right. How are we doing on time? I think we're doing kind of okay. All right. Any questions about apply? So this function that you write can be as complicated as you need. So like that question of before, how if you have a column that is like D and a number, you can write a function that parses it out. Just in here, you have to remember that when you apply the function row-wise, the entire row is coming with it. So the first thing you're going to have to do is subset the row for the particular column that you need. Or the other way of doing it is, this will just be more pseudocode. Clean 1 column. Takes a single column. So remember, you can also apply on a series on its own. So you don't have to run, if all you care about is cleaning 1 column, you don't have to write an apply that applies on the entire data frame itself. You can write a function that takes in a single value, and then you'll end up doing something like return single column 1 colon. So this is how we ended up saying D42 would give us 42, right? So I can then use the column and just run apply on an individual column, right? You don't always have to run and apply on entire data frame. So if you're really just writing a function to clean one column, extract the column and run the apply on the column. There's no need to say, hey, now I'm going to apply it to the whole data frame, because then you have to worry about, all right, so now this entire row came in. I have to go figure out or count like which position that row that I want my information, my function to work on, et cetera, et cetera. So just think about how you're writing these functions and how you're going to be using them. And then if we have time, we'll circle back. But the last thing is going to be circling back to group by. So we're going to be going back to the Gapminder dataset. Oops. The limiter is tab. All right. So we have our data set. I showed you before. We can say group by our year, pull out the life expectancy column from that, and then take the mean, right? So that's what we did all the way. That was the first thing that we did. What's actually going on under the hood is what you can think about is it's breaking up each unique value in this variable that we specified here. So you can say that this isn't actually what's going on under the hood, but in your mind, you can say it created a totally separate data frame. 1952 is gapminder .loc such that gapminder year is equal to 1952. Right, so we just have a data set of 1952 data. From there, we're taking the life expectancy column. So we just have the life expectancy column, and then running the mean. Right? And then we're doing that for every single unique value of year. So if if you're used to thinking in for loops, you can think of get me all of the unique values of year and then iterate through a for loop and run this calculation. And then at the end, stitch it together. That's essentially what's going on under the hood of when you run a group by. Let me go back to my notes. So mean isn't the only thing that you can do. So you can get, for each group, do a count, get a size, get a mean, standard deviation, et cetera, et cetera, et cetera. A cool thing I'll show you is describe. So you can say gapminder group by year and give me the life expectancy and then describe it. And that will give you, for each year, the count, mean, standard deviation, minimum, blah, 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 for that column, right? So it's a really quick way to get summary statistics that actually like break down your data set into smaller pieces.
Quick question about the previous command.
Yeah.
The colon there, technically,
This colon is a generic Python slicing notation. So I can have a regular list. And if I wanted to, just like I can get the first element of the list saying 0, I can say give me all of the elements up until the third element by saying 3, or I can say give me all the elements by saying colon. So yeah, so that's shorthand for all elements, and because it's to the right of the comma, it's all columns. So that's not Python, or that's not Pandas specific, that's in this realm of slicing notation in Python. Wait, say that again? Oh, yeah. I don't cover this in the tutorial, but yeah, so there's group by, you can do, so the way we've been doing it now is we've grouping by, we're making a, I forgot the actual term. I know in R it's called summarize. But you're doing group by, you're calculating an aggregate statistic, and so that's a bunch of values getting calculated into a single value, right? So group bys also have something called transform, which is doing a, you're grouping by some variable, and then the return is the same number of elements. So calculating a z-score is something that you would do a transform on. And then there's something called filter, which you can, for each group, do a filter and filter your data. So there are other ways that you can do that. And then time permitting, I can show you offline or in person. All right, so
If they had been set :8 instead of just per colon, would have been the first 7 columns?
yes, so if you had done that, I don't even know if that worked. Hmm. I will have to think about that. All right. So we can also write our own functions in using these group by stuff. So it doesn't have to be any of these summary statistics, although I'm going to use a summary statistic as an example. But you can use any vectorized function, for example, group by continent, get the life expectancy. So if you need to run any other function, so it's not dot mean or dot something that is already built into pandas, you can use ag or aggregate. They both are exactly the same, so ag is just shorter to type. And then in here, you can say, hey, I want to use the numpy mean function. Or this is exactly the same, aggregate. You can, I don't know of another std. Yeah. So I want the numpy standard deviation function, right? So you can put any vectorized function in there. It doesn't have to be one of the ones that I just listed before that come directly from pandas. You can write your own. So define my mean takes a set of values. So how do you calculate a mean? Well, you get the length of the values. And then the sum is use the numpy sum function just because it's vectorized, so you don't have to write like a for loop to iterate through each to get the sum. And then s divided by n. Right, so this is a function that I wrote, and it works on a vectorized manner because I'm using the numpy sum function. And we can use that right here and say my mean. Right? So you can create your own weird aggregate statistic or something, data transformation of like parsing some string or I don't know, some count. The limit is your imagination, I guess. All right. And then with these aggregates, what you can also do is you can provide multiple functions at once, and the only thing you have to do is give it a dictionary, so a set of curly brackets. And then since you're doing multiple calculations, so let's just do it this way. Actually, no. This is the old way of doing it. So if you give it a list of functions, so for example, numpy.count non-zero, numpy.mean, numpy.standard deviation. If you give it a list, it'll, for each group, give you the non-zero, the mean, or the standard deviation, whatever you wanted calculated. Right? So you can do that all in one go. And then again, you can put a set of square brackets here and just break down your data set as far as you need. If you want to use, if you want these column names to actually like be meaningful, the old way of doing it, which is no longer will work, is you can say number. So instead of a list, you give it a dictionary, num count. Mean standards TD. Right. So you can rename these columns. The only problem right now it's going to say, hey, this won't work in the future. So I had to last night go figure out how this will work in the future. So the way this will work in the future is you give it the old notation, which is using these square brackets. And then you actually say rename to rename your columns. So columns, COLUMNS. Yes. How do you want to rename the column? So count non-zero. I don't know why they made this not work because this is actually way more typing. Mean will be called average. STD will be called dev. All right. Oh no. Oh no. Oh wait, what? Count. Oh, it's end count. Oh, whoops. Sorry, I meant to undo that because you're not allowed to do that anymore. All right, there. And then we can clean this up because this is pretty messy. All right, so you can also reset the index at the end just so you get a nice flat table that I'm very used to looking at. So the last thing, group by pandas. Just for time constraints, which I guess I knew that I wouldn't have time to do this, there is a page called group by split apply combine. And so I just showed you aggregation. So that is calculating, taking a bunch of values and computing a single value as its output. There's transform, which if the number of inputs is equal to the number of outputs, and then there's filter where it's somewhere in between. I would say you should look through this. So calculating a z-score is an example where the way z-score is calculated is you calculate the average of something and then you run, how do you calculate the z-score? It's some function that requires the average, but the result is each element gets rescaled such that the mean is 0 and the standard deviation is 1, right? So each value will get a new value. So that's what transform means. It's doing a one-to-one mapping. So you don't have to calculate the z-score for the entire data set. You can break it down by year or continent, et cetera, et cetera. And then filter is for each group, give me the values where the life expectancy is greater than 50, right? So you can do aggregate statistics like that to return something back to you. And the reason behind, or one of the reasons behind, having that under the group by is if you think longer term into distributed systems, the syntax will be almost exactly the same, where you can say, hey, I have this, 5 billion row data sets sharded across 5 computers. I can say group by this, and then the syntax is exactly the same of doing these aggregate statistics. So the more familiar you are with group by, it'll very, I wouldn't say easy, but grasping how distributed systems work will be less difficult because at least your code will not really change. All right. So the last bit is stuff I am not going to type, but it is essentially a segue of to hopefully you guys have learned something about data cleaning. And then so at the end of your data cleaning process, you typically want to fit a model of some sort. So this would be a segue into how would you fit a model. So there are two major packages used to fit models. So there are stats models and sklearn, both of which I'm pretty sure were a tutorial in this conference at some point. And so this is generally how that works. So we have pandas, we're importing pandas because we're working with data frames. I'm using Seaborn to load up a data set. All of these things also have built-in data sets with it. I just ended up using the Seaborn data sets because at least I definitely know this is a regular pandas data frame. A lot of the, especially in scikit-learn, they're not like, the data sets that come in scikit-learn are not like regular data frames. So you have to, their examples are a little different. It's not as simple as plug and play. So I tried to give you an example of what it would be like if you worked with pandas data frames from the beginning and now you want to fit a model. So there's two different ways you can use stats models. There's a regular API, and for the R-like people, there's a formula syntax. And so this formula syntax will look very familiar if you've fit a model in R before. So this is our tips data set that we've seen. And so to fit a regular linear regression, stats models has a function called OLS. So we're doing regular ordinary least squares regression. Their naming convention is a little weird. They use endogenous for the response variable, or sometimes called the dependent variable. I personally hate the word dependent and independent variables just because that sort of like conveys that the two things are related, and when you fit linear regression, it's one of the assumptions is they're not dependent, so I don't like using that term. And then there's another variable where you specify all of the predictors of your model. So here we're going to say, how does the total bill affect or predict the tip that you're getting? So that goes into the model object. All that does is set up the model, so you actually have to say model.fit. Typically, you'll see people just say .fit like right there directly, just chain it together. But a lot of the tutorials you'll see will just do it in multiple steps. So you get a set of results after you fit your model, and to look at your results, you say results.summary. And here, if you've ever seen statistical output, this is what you get when you run summary. This is sort of the benefit of using stats models because you actually get this set of results. If you end up using scikit-learn, you don't get this. And it's just because there's two schools of thought of how these things are working. Stats models are, you're actually fitting models as like a statistician, versus scikit-learn is more of you're trying to do like internal validation through like cross-validating and stuff like that. So so scikit-learn is really good if you're trying to do cross-validation and all of that stuff. If you're just trying to fit a model like a regular statistician, you know, it's easier to get these tables out. Yeah.
That's results.summary. Is there a way, that's a complete exhaustive list of all the objects created by the model?
No, this is not an exhaustive list of the model.
How would you see everything created by the model?
Oh, I need to run this, that's why. So results.tab, and then you can see everything that's in there. Yeah, so I would use tab complete to help you get everything. So here's the lowdown on how you interpret this. You have a table of coefficients. In this case, we have total bill, and then a coefficient here. And because this is linear regression, the way you would interpret this is saying for every 1 unit increase in total bill, so for every, in this case, dollar, so for every $1 increase in total bill, the tip that the person can expect will increase by essentially 14.3 cents, right? So I guess that's good. People are roughly tipping 15%. Although tipping can be a whole other debate on whether we want to have tipping in this country. If you just want the parameters, you can say results.param. And so if you don't want the entire table of results and you just need the parameters to go on with your work, you can say results.param to just get the coefficients. If you need multiple variables, pretty much the same thing. So in this case, this is multiple continuous variables. I haven't shown you a categorical variable yet. So if you're doing a multiple continuous variables, again, put it in a set of square brackets. Just realize that in this case, you need 2 square brackets. Don't remember the exact reason for that. But the rest of the model will look exactly the same. Once you create the model, you fit it, you run summary, and you get your summary statistics. And so you can see the coefficients will change because we've essentially adjusted for another variable called size. But the interpretation for each variable is roughly the same. So for each 1 unit increase in size, so for each additional person that joins the party, the tip will increase by 36 cents, assuming that the total bill is the same. And then for total bill, you can say for each $1 increase in total bill, the tip will increase by 10 cents, assuming the size is constant. Yeah.
It doesn't create another object that's like the vector of residuals or anything like that.
Oh, you can totally get the residuals and all of the other stuff.
Without calculating it yourself.
Yes, yeah, it's all in there. It's somewhere in there. So if we look at the tips info, you'll see that we have a bunch of categorical variables. I guess it's almost easier to just jump to the formula syntax if you're working with categorical variables, because the formula syntax will understand that this is a categorical variable and create the dummy variables for you. So what is a dummy variable? So let's say I have a categorical variable like sex, male and female. It would make no sense as a model to say, let's say female is 0, male is 1. It would make no sense to say, like, for every 1 unit increase in sex, something happens. Like, what does that mean, right? So it has to be a categorical variable, and so that's why it's a categorical variable and not a continuous variable. But how do you actually put that into your model? So you end up creating what's called a dummy variable. So what ends up happening is you create a separate column called male and a separate column called female, or you create a new column for each unique value in your category. So in sex, it'll be one category called male and one for female, at least in this data set. And then if the person is male, the person will get a 1, and then female will get the column, the value for female will be 0. And if the person is female, the female value will be 1, and the male value will be 0. Right? So you created a new set of columns for each category. And typically with dummy variables, you end up dropping one of them just for multicollinearity. And so you can essentially, instead of having 2 columns for male and female, you really just need 1 column for female, because if the female column is 0, you can already assume that it's male, right? So that's why you'll hear when you start fitting models, and this isn't really a stats class, you'll create n-1 dummy variables. So that's what this model will actually give you. So using the formula syntax, so if you've used R before, this is exactly how you would specify a formula. You have a tilde. The thing to the left of the tilde is your response variable, so tip. And then the thing to the right, you literally add the variables together. So we're trying to say we're predicting on total bill, sex, smoker, and size, right? So total bill and size are continuous variables. Sex and smokers are going to be categorical variables. If you're using the formula syntax, be mindful it's OLS in lowercase. If you use OLS in capital case, it will be using the previous syntax. So you specify the data, but then you fit it, you run the summary, and then you get this nice table. And so here you see sex as a female. So this is essentially because male got dropped because it's n-1 dummy variables. This is saying that if the person is female compared to males, then the tip will increase by 2.7 cents. So females are, assuming everything else is the same, tipping 2.7 cents more than males. Right? There's issues with interpreting that, which we'll see looking at this p-value and the t-statistic, but this isn't a stats class. So, but then, so you can see for smoker, so smoker is the person a smoker, yes or no? So because this is actually nice that it tells you what the target variable is. So the reference variable is yes. So when the person is not a smoker, the tip will increase by 8.3 cents. Right? So that's what fitting a model will look like using stats models. All right. You can do the same thing with logistic regression. So linear regression is when your response variable is an actual continuous variable. Logistic regression is one type of method if your outcome is binary. So in health data, like did the person die, yes or no? So if you have a binary variable, that's when you would use logistic regression. So in our Titanic data set, we have a column for survive. Did the person die, yes or no? The function you will use. So I'm just using the formula syntax. I tried to use this like the non-formula syntax, and it became like something I didn't want to figure out at 2 in the morning. So the formula syntax, oh, another side note, yeah, this is totally not a stats course that I'm trying to give you, because there's something like you have to create an intercept that this isn't doing, and there's a whole bunch of other stuff. So this isn't totally like a valid statistical thing I'm doing. More just showing you how you can continue on with your pandas knowledge. So the formula syntax is exactly the same as before. Response variable to the left of the tilde, so did this person survive, given sex, age, fair, and deck. And so now you can see it creates this table of results. You can see deck had a lot of different values in them. So there was 1, 2, 3, 4, 5, 6. So there are 7 values for deck, but we have 6 in our table. Oops. Uh-oh. Uh-oh. Where'd it go? Where'd it go? All right. But when you're doing logistic regression, it's much harder to just take this table of results and interpret it. When you are working with logistic regression, this isn't a stats exam, so I'm not going to explain why, but you have to exponentiate your values. So you can run the numpy exponentiate function on your parameters, and then you can say something like, for example, on age. So for every 1 unit increase in age, the probability of you dying, in this case, quote unquote, increases by 0.95 no, wait, that's wrong. The odds of you dying become 0.95 times the chances of you. Oh, wait, hold on. How do I interpret this? For every 1 unit increase in age, the odds of you dying are 0.95 times the odds of you not dying. So when it's less than 1, it's actually protective. So apparently, the older you are, the very less likely you are to die. But if you look at the coefficients, that's probably not something that you can really like interpret very well. But yeah, so just keep in mind when you're looking at logistic regression, you have to exponentiate the results, and you're actually interpreting them as odds ratios and not like we did with linear regression. Last example. So how would you do all of this in scikit-learn? I only really had time to do this for one example for tips using linear regression. So scikit-learn, you import the linear model if you're trying to do a linear regression. Do you have to create dummies for this? Oh, I guess you do. So here, because scikit-learn essentially expects a array of 1s and 0s essentially, you have to manually create dummy variables. So in Pandas, there's a function called getDummies. You can give it the column that you want to create dummy variables with. I am dropping the first one because you only need n-1 dummy variables. Certain statistical methods, you actually just keep all of them, so that's why that parameter is there for you. And then so we get a new column for sex, whether this person is a female. So if the person is female, they get a 1. If it's male, they get a 0. To create the linear regression in scikit-learn, we create this, we initialize this linear regression object. We give it the x and y's, so the x, or our predictors, are going to be the total bill, the sex dummy, the size. The y is going to be the tip column. We feed in the x and y vectors into the fit, so we have to fit the model. And then we don't really get that nice table of results anymore with scikit-learn, so you can get the coefficients by running coef underscore to get the coefficients. And then just because this vector of numbers is kind of useless without some kind of variable name associated with it, you have to manually essentially tie the variable name back to it. So if you want, you can say for every 1 unit increase in person at the table, the tip will increase by 19.3 cents. All right, that's all I had for you. I guess I can circle back to apply. Is there any other questions before I just go on? Yeah. Oh. I guess I didn't test that out. Yeah, I can't explain that. Why it didn't work in Python 2 or 3. The general rule of thumb for anyone who I don't know, is listening to me. If you're starting a new project, the rule of thumb is start the new project in Python 3, but if you already have an existing project in Python 2, you don't have to convert it over to Python 3. Just know that Python 2 does have a has an end date. There's an actual web page that is when is Python 2 ending? And there's literally a website that is counting this down. So, take that, that's why the general rule of thumb is if there's a website counting down something, you should probably adhere or listen or do something about it. All right. So, yeah, it's. Yeah. All right.
I would say most of the ones that all of us have heard of have. There may be. So my suspicion is if there isn't, then it might be, like a one-person project or something. But yeah, I mean, the writing is on the wall. For everybody.
Yeah. Um, what methods have I done before that Python has saved me? So I got my master's in public health and epidemiology, and so a lot of the data sets that at least we've worked with are these national representative surveys. So a lot of data cleaning was really just recoding in SAS. Essentially what Python allowed me to do, but that's also just because of the order I learned things, so it's not really just Python specific, was getting a random data set off the internet or scraping a piece of data. That's something I don't think I would have been able to do in SAS. If I did, I don't think there would be documentation on how to do that in SAS. So, stuff like we have, so we work with a lot of GIS data in my lab, and so there's going to be like, oh, we got this data set with like state names fully typed out, but this other data set is state names and there's 2-digit code. Like, how do we find a table in between to link them together? So that's sort of what Python has allowed me to do, is like, oh, Wikipedia is great for that type of information. You scrape the data off of Wikipedia, and now you can do a join, use that as an intermediate to join all your data together. So that's stuff that Python has allowed me to do, not to do. Don't write for loops if you can help it. I think like a few years ago, like in like a Pi Gotham, like Jeff Reback, like one of the contributors to Pandas, he actually wrote a talk that was like how to make your code slower. And like it started off with like write an apply, and then at the end is like use the iter rows on a data frame to actually iterate through the rows to write a for loop. So typically if like I would say like this apply function thing is really important, because chances are when you're cleaning data, you're not cleaning one cell, you're cleaning like the entire row or column at once. So the to do or what not to do is don't write a for loop, especially if each row is completely independent of another. That's usually a good sign. Sometimes you have to, okay? But like try to understand how apply works, and that will make life much easier down the line, because it will be like all of this stuff like numba and all of those optimization things that make your code like faster, like they all work on functions. So if you already have your code written as a function that is applied to your data set, you know, you can do those like speed optimizations much faster. But yeah, so like I was gonna show you like one more thing that you can do with apply, is we have this function that we wrote that is x, y, and it takes two values. But we can't actually say like df a, df b, or we can. Why does that work? That's not supposed to work. Oh, I know why that works. Okay. Now I can't think of a good example. That's interesting. I don't know what to do.
Not really annoying if you had a lot of rows, right? Or a lot of columns.
Yeah, well, I was trying to, hold on. Let me see if I can look this up. This should be pretty quick. Okay, anyway, I don't know. So if you end up with a function that isn't vectorized for whatever reason, like the reason is like this right here actually does a vectorized calculation. You can use numpy has a way to turn any function into a vectorized function, and you use this notation called a Python decorator. So what this will do is the decorator is essentially at and then something in front, right in front of a function definition. And what this will do is it will take this function and vectorize it. So if I had manually calculated like an average function using a for loop or something that's not made to be worked on arrays, you can say at np.vectorize, and then it should work on an array of data. I realize the example is probably failing and I have to make some edits, but that was like the last thing I wanted to quickly go over is if you do have a function that's not vectorized, and if you don't want to use the apply way or rewrite it so like the first thing it takes is an x, the entire row, and then you have to rewrite the code underneath, you can say np.vectorize and then just pass in your parameters that way. So, but yeah, that's all I want to go over. I'm happy I got through everything because it was a lot of stuff. But yeah, so keep with it, I guess, since all of you guys are here because you're very new to pandas. So it would be about 3.5 years ago, as I was essentially like sitting there like in my own software carpentry tutorial, learning about like how to do analytics. So, practice, 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 and you know, you'll get it eventually. All of this stuff really is like kind of an art. The more I think about it, you are taught all of the core fundamental pieces. It's with practice you'll get used to chaining them together to get what you need. So.